Good morning, good afternoon, or good evening to everyone.
Good evening. Good evening and good morning.
Thank you. Depending on the world, the part of the world you are. So I
Yes,
hope
that's right.
you are doing well. Okay, let's start this last day session with the talk by Lucia Falzon on time and sequence in network of social interactions. Please, Lucia.
You can see my screen?
Yeah, yes, we can.
Okay. Okay, well, good morning, good evening, and greetings from Australia. So I'm going to talk today about time and sequence in networks of social interactions. So this work is work that I've been involved with over the last few years with various collaborators. Oh, this is jumping around. Let's go that way. And essentially, I'm going to just, in the introduction, I'll just briefly talk about algebraic structures for static networks, and we've seen quite a few talks that talk about that, so I won't take a lot of time doing that. But then I will talk about extension that we did a few years ago to networks of time-ordered relations. And then I'll finish off by talking about measures in these new temporal networks. So, so this work has been motivated by the growing requirement to understand dynamic interactions on social networks. So, in particular, of a lot of interest lately have been discussions on social media networks. And because these are not relations in a normal sense, they're essentially we're talking here about sharing discussions, sharing posts and that sort of thing. The time is really of the essence. These are highly dynamic interactions. And in particular, if you're talking about diffusion of information over these networks, then the temporal ordering needs to be taken into account. And even if you talk about networks of longer type of relationships, so in particular here, we were quite motivated by Moody's work in 2002, where he was looking at networks of relationships and the transmission of sexually transmitted diseases. And of course, the ordering of those relationships is important if you're trying to track a particular disease. And this has become quite pertinent these days with tracking COVID. So as I said, in 2013, we extended the sort of the static algebraic structures to the dynamic case. And then in subsequent papers, we looked at concepts for network measures in these types of networks. So just to show how to sort of develop more of a concept. So a static network is essentially a Boolean kind of network. So edges represent relationships that are either present or absent. Whereas these dynamic networks that I want to talk about, the edges are there for over finite intervals. And it could be a set of discrete intervals. So people are in communication or in some sort of short-term relationship over a finite interval of time or several finite intervals. So starting with the static network, first of all, we consider a set of relational types. So you might have a network that represents friendship between people and another one that represents collaboration. and each one can be represented by a directed graph over a set of nodes n, where E is a set of edges, and each edge is an ordered pair from n. And then for each relation type, we have an adjacency matrix. And then we can compose, as several people were showing us over the last 2 days, you can then define a relational composition. So you can compose two relationships, and you have a new network, which is essentially the relationship A composed with the relationship B. And you can define this sort of composition as a product of the two matrices. And then you can also define a union of these two networks A and B on the same node set, and that's defined as pairwise Boolean addition. And you can also define a natural partial order, and this is how you develop the sort of a network structure which we've seen before. So here in this case, the matrix AB is essentially representing a composition of relationships. In this case, for example, you might say that the ijth entry of matrix AB represents the fact that, well, that I is a colleague of J's friend. If you're only multiplying matrices of a single type, then the multiplication of the matrices give you the walks in the network. So you know, if we just square the matrix, we get all walks of length 2, and then if we do it again, we get length 3, and so on. And in other words, in static networks, in order to construct walks, you only need to determine node adjacency. And as I'll show later on, in temporal networks, this is not the case. So when you're considering the time order on a relationship edge, then it's not enough to have node adjacency in order to construct a walk. And as an example of a measure on a static network, of course, we say that node J is reachable from node I in k steps or less if the ijth entry of the kth order matrix is 1. And here the kth order matrix is essentially just the union of all the matrices up to the kth power. Now, traditional SNA measures are used to understand and describe social networks with the assumption that all the ties, well, all the ties that are present exist concurrently. So if a tie is there, it exists concurrently with all the other ties in the network. And so time is typically not really considered, except in the case where if you're looking at longitudinal studies, and then you might take a snapshot of the network over various times and see how the network is evolving or changing, whether ties have been created or dissolved, and that sort of thing. There are also relational event models in which you can look at the effect of past interaction history in order to predict future ties. So in those cases, time is obviously considered, but what I'm talking about here is a little bit different to these cases. So, first of all, we define a tie to be present over a certain interval, uv, which is u is called the onset of the interval, and v is the offset. And this interval is contained in some observation period that is predefined. Then we can define a set of disjoint and bounded temporal intervals, E, as in this way. So essentially, it's a set of intervals. And doing this, we can then construct what Gondran and Minu call a generalized adjacency matrix of this dynamic network. In other words, the ijth entry is essentially the set of intervals over which I and J interacted, or over which they had some sort of a relationship. And that's essentially what is the basis, I guess, for this algebra. So, and we used Moody's paper in 2002 in order to sort of build the intuition for this kind of algebra, so for the representation, and also to develop the composition operation for these networks. Essentially, the idea is that all previous context has implications for all future interactions. So if you think of this in a disease kind of way, so if we're trying to detect who might have been infected by a virus, for example, COVID, we need to take into account all of the previous relationships. And clearly, the order in which the interactions happen is important, because that's what actually gives us the path of diffusion. And so what we do is we construct these things. We develop a matrix composition that takes time into account, and the result of the composition gives us the time over which diffusion could have happened. So the result of the composition is not whether a relationship is present or absent, but it's whether it's the time over which diffusion could have happened, or transmission, disease transmission, or information transfer could have happened. So this is the definition of the composition. Essentially, we have these two interval sets here, and we're trying to compose them. And so we essentially here we're composing two sets of intervals, and we do a sort of a pairwise composition for each pair of intervals for each interval in each of the two edges. And we define it in this way. So the onset is the maximum of the two onsets, and the offset is essentially the offset of the later of the two intervals in this way. And this is sort of what it looks like pictorially. And then we also need to define some kind of a union. So it's like an addition operation for our algebra, and that's just a plain pairwise union of the intervals in the two sets. And that definition is essentially here. So then, having defined these two operations are analogous to multiplication and addition, say, or union, we then are able to develop algebraic structures, which are useful for computing path-based measures in particular. So, and I'll talk a little bit about this in a minute, but the measures that we're interested in these networks are path-based measures because of the temporal nature of these networks. It's essentially we're looking at where information or disease are transmitted. So we're looking at diffusion paths. And in our paper here in 2013, you can see all the details, but we show that this is essentially a left diode. And just as we do in the static networks, we can define the appropriate matrix operations to construct paths. To construct paths and walks, and so just as we do in the static networks, essentially we get an equivalent. Now that's fine if you're talking about if you're not worried about the whether the information or that you're passing on, whether that has a decay factor. So certain types of information become stale after a certain period of time. So we are here interested in looking at more general types of compositions. So we introduced this time lag factor, delta. So in order to construct an algebra out of this, we have we use this idea of a translation. So we essentially extend the second interval, the offset of the second interval of the first interval, sorry, by delta, in order to essentially what we're doing is we're imposing a constraint and saying the information is only good for delta time. After that time, it becomes irrelevant, or the disease has lost its potency. So essentially what delta does is it constrains the opportunity of transmission. And we show that by setting delta to its maximum, the length of the whole observation period, essentially this becomes a generalization of the previous case of, Moody's example for composition. So we can choose delta so that it fits the medium that we're interested in. So if we're looking at very hot gossip, so typically, for example, in social media information, where information becomes stale very, very quickly, then we choose a very short delta. In other cases, we can choose a longer delta. For example, for email traffic, we might choose delta to be a week or something like that. So depending on what we're modeling, we choose a different type of delta. And because now we have added this complication of a translation, and essentially we've now turned the composition operator into a one-sided operation, and so that introduces a complication in algebra. And in order to get around that, or to handle this, we had to introduce endomorphisms into our algebra. So what we do is we have this idea of a one-step endomorphism. So we essentially extend our interval by 1 in order to construct one step in our path. And then we keep doing it again, but only from one side, you see. So in that way, we get all the 2-step walks, all the 3-step walks, and so on. And each time these walks, one, that is they conserve our time sequence, and 2, they add this delta to the end of the first interval. So it handles those 2 conditions that we wanted. One is to make sure that our path obeys time sequence, and 2, that we have this we've incorporated delta, which represents the decay factor. And so now we can start thinking about measures in these networks. So in social networks, in static social networks, there is this notion of centrality, which is essentially looking at an individual's importance or ranking in the network, and it's typically based on their structural position in the relationship network. So, for example, degree centrality, which you might know, or eigenvector centrality, these are particularly suited to static relationship networks. But when you start considering diffusion networks, what you really, the measures that are most useful are the path-based measures. So such as the measures like reachability, which I talked about when I was talking about the static network. So essentially you're measuring the proportion of actors that are reachable from a particular node. This idea of closeness centrality, so you're measuring the shortest distances from one particular node to all other nodes. or betweener centrality, which is measuring the proportion of shortest path that goes through a particular node. There are others, but those three are just good examples, I think, and they're the ones that are very widely used. So essentially, what our message is, I guess, that in when you're considering temporal flow, you actually have an induced temporal direction. Essentially, the time imposes an additional direction on your network. So whereas in the static case, the reachability of a node depends solely on the network structure. As I said, it really only depends on node adjacency. In the temporal case, we actually, it's not enough to just consider node adjacency. You also need to ensure that sequential edges satisfy the time constraints. All sorts of interesting things happen as well in the temporal case. Like, for example, in static networks, we know what the shortest length path is. It's essentially the path that has the least number of steps. But in temporal networks, of course, now you can also define a shortest time path. So the time, that path that has the shortest duration. So there's an added dimension, I guess, once you consider time. I've just to sort of try and illustrate what I was talking about, I've got a few examples here. Here we're looking at reachability, for example. So we can consider reachability using time, so using this notion of sequential interactions. And we can also do the same thing, but with ignoring time completely. So in the stop chart, you can see the black line there. That's essentially, if we ignore time completely, what it's saying is it's every node in this little network, which is quite a small network. It's about 120 nodes, and it's essentially an email network. And what it was data collected over about 8 months. So it's about 8 months worth of data of emails between people in an organization. The black line is actually if we ignore time. So every node is reachable from every other node. Once we introduce time, for a start, we have two types of reachability. We have in-reachability and out-reachability. So one is the number of nodes that I can reach, and the other one is the number of nodes that can reach me. And so we have two of these things. But not only that, but you can see from this chart down here that when in the static case, every node is reachable from every other node in 3 steps or less. Whereas in the temporal case, sometimes we can go up to 6 steps, and there are some nodes that can never reach all the other nodes in the network. So that gives us it distinguishes time ordered networks from static networks. Similarly, for temporal and static betweenness, if we ignore time and we look at the rankings, we see that the ranking of the nodes changes. A couple of nodes are still at the very top for both static and temporal case, but the majority of them actually change the ranking. So it is important to consider time. And the last example is for brokerage. Brokerage is quite interesting because essentially in the static case, brokerage opportunity is purely enabled by the actor's structural position. So in this case, the broker is B, and essentially the broker has got an opportunity of brokering just purely because of their position in the network there. Now, when you consider time, we have 2 different types of brokering. We have in the top case, the broker is essentially controlling information between X and Y. In the second case, the broker has actually introduced, if you like, X and Y, so that they've enabled the communication between X and Y. And here time is of the essence, because in the first case, the interaction between X and B would have had to happen before the one from B to Y, in order for you to have this continuous information diffusion through B. In the second case, then we need the edge that connect X and Y to happen after the interaction between B and Y, which in turn must happen after the one from X to B. And this is all sort of described in this paper on brokering. Just to conclude then, time-ordered operations yield the transmission times for direction for indirect operations. So A can reach B through some time-ordered path by time t. That's what we get when we have the matrix operations. As in static networks, we may also compose different interaction types, just like you can do in static networks. You can say that A is a colleague of J's friend. Well, here you can say A emails B and subsequently meets with B, and enabling a potential transmission from A to C via B over some particular time interval. Time respecting paths are intrinsic to flow, connectivity, contagion, as well as more abstract notions of spanning trees and cuts. And these concepts are actually essential for modeling social processes, because social processes, by their very nature, have to consider time. And so this algebra is really very important, I think, if you want to consider social processes over networks. And the last point is, because the data used here are actual records of interaction, so they're not based on survey responses, they're actual records of interaction. So here there are no assumptions of homogeneity. Essentially, we are considering every communication observation. And I think I'll end there, and I'm happy to take questions later on. Thank you.
Thank you, Professor Falzon, for your nice talk. Professor James will talk about transformation representations of semigroups. Please, Professor, you can share your slide now.
Okay, you just have to give me a minute to find my thing. Okay, can you see this?
Yes, it's fine.
Okay. All right, so it's 25 minutes, right? Okay.
Yes.
All right, well, first of all, thank you very much for the opportunity to speak at this conference. So this is a project with these people on the screen here. This is, in fact, entirely a lockdown project. All of this started after COVID, so we've been emailing and communicating virtually, but we haven't got together and done anything together. But anyway, so what's the basic idea of this? It's to well, in terms of notation and setup, we're going to fix an integer n, and bold n is going to denote the set of the first n integers. And we're interested in the semigroup of all functions from this set to itself, which is called the full transformation semigroup of degree n. Okay, all functions from the set 1 up to n to itself. And under composition, it's a semigroup. It's a basic result that any abstract finite semigroup embeds in some Tn. So any semigroup whatsoever can somehow be thought of as a semigroup of transformations. And that leads to a natural definition, which is the degree of a semigroup, and that's just the minimum such n. Okay? Every semigroup is some kind of transformation semigroup, and the degree of the semigroup is the smallest such n. So it's the minimum M, such that S embeds in Tm. All right, and that all leads to a natural problem. You have a favorite semigroup and you try and find your degree. All right, that's what the talk is all about. So why might you do this? I hope everyone at this conference would agree that this is enough of motivation. It's a fun problem to work on. If you have a family of interesting semigroups, then trying to find their degrees generally leads to an interesting combinatorial problem, integer sequences and so on. And it's quite a challenging problem. So even for relatively simple semigroups, it can be quite difficult to calculate degrees. A practical reason for doing this is to do with computation. So the GAP computational algebra system is really set up to work well with transformation semigroups. So if you have a semigroup you're interested in, if you can represent it as a transformation semigroup, then GAP can compute with it. And of course, the smaller the degree, the better. And it actually ties in with an interesting philosophical idea in semigroup theory, which is that if you take all of the finite semigroups and put them in order, all those of size 1, then all those of size 2, then size 3, then size 4. By the time you get up to the semigroups of size 10, let's say, almost all of them have a certain property that could be taken as a definition of a boring semigroup. They're three nilpotent. But if you instead take the semigroups and order them differently by degree 1, then degree 2, degree 3, etc., then each bucket of semigroup seems to be mostly interesting, which is quite nice. And if there was more time to speak here, I'd be going through some existing results from some of these authors. But suffice it to say, quite a few people have worked on, have done some quite interesting works on this problem. So it should be said that a lot of these people have worked on the corresponding problem for groups, where you look for the smallest n such that a group embeds into a symmetric group of degree n. So the particular project that I'm talking about today actually started from an accident in GAP, where I was computing something, and when I pressed the enter key, I expected to get the picture on the left, and instead was shown the picture on the right. And this led to a little paper, 5 pages in experimental mathematics, which you can look up. It's quite an easy read, which explains what the problem I was working on was and what the accident was. And it led to a fairly surprising result, or at least a result that was surprising to me, which is that the degree of a certain semigroup called a sandwich semigroup is quite small, quite a bit smaller than I was expecting it was. The best that we could say before this was that it was at most n to the n, but now we know it's at most 2n. And even when you take something like n equals 100, this is comparing something like 200 to a Google, or even bigger than a Google. So chances are I won't be able to say much more about this, but I have some slides at the end in case I somehow finish quickly to get back to this. But what I want to mostly talk about today is some sort of simple kinds of semigroups, at least they're simple to define, and how we can go about finding their degrees. So the first is called a left zero semigroup. This is just a set, any set whatsoever, and the product of 2 elements is always the left element, right? So x, y is just always x. This is an example of a band, a semigroup in which every element is idempotent. Vicky mentioned idempotence yesterday. Idempotence just means that you square the element and you get itself. And of course, if you put x equals y into xy equals x, you just get xx equals x. It's also easy to convince yourself that any 2 left zero semigroups of the same size are isomorphic. Any bijection between the 2 sets will give you an isomorphism. So there's really, up to isomorphism, only 1 left zero semigroup of every size. So for any element p, any integer p, sorry, we'll fix a left zero semigroup LP. And David Eastdown, my thesis advisor, calculated the degree of a left zero semigroup back in the early 90s. Okay, and that gives us an integer sequence. We've got the degree of L1, the degree of L2, etc. So once we know what a left zero semigroup is, there's no sort of more imagination required to come up with the idea of a right zero semigroup. Here, xy is always going to be the right element, xy equals y. Isdan also calculated the degree of a right zero semigroup. And the obvious question you're probably all asking at this point is, are they the same? Okay, left zero semigroups and right zero semigroups are essentially just left and right-handed versions of the same thing. Maybe their degrees are the same, and we'll see what the answer to that is soon. Another simple semigroup, maybe even simpler, is a null semigroup. This isn't a semigroup where every element is a left and right zero, but it's a semigroup that has a zero element, and the product of every two elements is that zero element. So if you write down the multiplication table of the semigroup, it's just zeros everywhere. So zero is a fixed element. It's a multiplicative zero. And in fact, in this case, it's the only idempotent, right? Because if x squared is x, well, x squared is also zero. So x is zero. So we ask the same question: what's the degree of a p element null semigroup? And for whatever reason, this hadn't been calculated, not because it's extremely hard, but because, I don't know, maybe no one thought of doing it. But this other kind of simple semigroup also has an unknown degree, and it's a little bit more tricky. So this is a rectangular band. These are also very common semigroups. You basically this time have two coordinates. So I've got an L coordinate and an R coordinate, and the product sort of works where you multiply two pairs and you just ignore the middle. So you get the left part of the left factor and the right part of the right factor. Okay. And if you think about it, what we're doing in the first coordinate is we're doing multiplication in a left zero semigroup, AB equals A. And in the right coordinate, we're doing the multiplication in a right zero semigroup. So a rectangular band is just actually a direct product of a left zero semigroup and a right zero semigroup. Okay, if BY is AX, then the product just gives us AX equals AX. So every element is an idempotent again, hence why we call this a rectangular band. And of course, we want to know what the degree of a rectangular band is. You'll notice here that the dimensions of the rectangular bands are important, P and Q, not just the size of this thing. So this is an array of numbers, not just a straight integer sequence. This was not known previously, and this was a bit more tricky than the others. So I want to say a little bit about transformations so that we can understand how to attack questions like this. So the first thing is that there's a convenient way to express a transformation. We're probably all familiar with permutations, where you list the elements 1 up to n, and then you list their images below. But with transformations, sometimes different elements go to the same place. So it's actually more convenient to just call 1, 2, 3, for example, a set A1, and say all of those points go to a single point x1. Okay, so in this case, 1, 2, 3 is the set A1. They all go to the point 2, which is x1. All right, and pictures like this are sometimes more conveniently drawn in sort of triangular fashion, like so. And 3 parameters associated to a transformation are important in all of this. First is the image, which is just the common thing of all the points in the codomain that are actually mapped to by something. So in this case, it would be what, 2, 5, and 7. That's a subset of bold N. The kernel for us is going to be a partition of bold N. Basically, we get all the points that map to the same places, and we put them into blocks. So A1, A2, and A3 are the blocks of the partition kernel F in this case. And then finally, we have a single number, which essentially tells us, well, it's R, but it's basically the number of triangles or the number of points that are in the image of the transformation. Okay, and well, all of the simple semigroups that I discussed before had either all idempotents or a unique idempotent. So idempotents are important, and it's good to know when a transformation is an idempotent. So imagine we looked at this transformation up here, F, and we wanted to know if it's an idempotent. So we want to do F composed with itself and see if we get F back. Okay, now consider a point in A2. Imagine we apply F to that, we'll go down to x2. Now we apply F to this again. well, x2 is up here in A3, so after we apply f a second time, we're going to get to x3. Okay, but that's not where we got to just from one application of f. So f squared is not equal to f in this case. And the problem was that when we got down to x2, it was in another one of these A sets. All right, so where idempotent provided that the image of, say, A2 is a point in A2. So xi has to be in AI. And here's an example of a transformation where that is the case. And you can see basically all of the triangles kind of map to something inside the triangle. Okay, so let's think about left zero semigroups. What's the degree of a p element left zero semigroup? This is a good question, and it turns out that there's a slightly indirect way that we can answer this. Rather than fixing p and saying what's the minimum n that contains a p element left zero semigroup, we're going to fix n and say what's the biggest left zero semigroup that Tn contains. And if we can answer this second question, we can answer the first question by just, if you've got a left zero semigroup of size 1,000, you look for the first time you find an n that contains a semigroup of size at least 1,000. Okay, we'll go through a couple of examples in a sec that'll make this a little bit clearer. But for the moment, let's just imagine we want to answer this second question. So let's imagine we've got a fixed n and we've got a left zero subsemigroup L of Tn. Okay, the first thing you do is you show that all the elements of L have to have a common image. This follows from considerations of Green's relations, which I don't want to go into too much detail here, but let's say the image of all the elements of our left zero semigroup L is x1 up to xr. Okay, good. Well, remember every element of a left zero semigroup is an idempotent, so they'll look something like this. All right, we've got x1, x2, etc. fixed. We know that x1 has to be in the set A1. So somewhere here we've got x1 mapping to x1. We'll also have x2 mapping to x2, and in fact, all the rest of the set 1 up to n can go to any of these R points we want. So we've got complete freedom to choose them to create an idempotent. And if you do some counting, there's R to the power of n minus R such idempotents. Okay. It turns out that these all form a left zero semigroup. So the biggest left zero semigroup that has whose all elements have this image is going to have size R to the n minus R. Okay. Now, what's interesting about this is that this number depends on R and n, of course, but it doesn't depend on the actual elements of X. So all that matters is the size of this. So we can let R vary, and we get different sizes, 1 to the n minus 1, 2 to the n minus 2, etc. And if we find the biggest one of these, that'll be the biggest left zero semigroup that Tn contains. So the biggest left zero semigroup in Tn is just the maximum value of R to the n minus R as R ranges over all the numbers from 1 to n. Okay, you can calculate these numbers quite easily, and this tells us, for example, that the biggest left zero semigroup in T10 has size 4096. Okay, so let's say we wanted to know the degree of L1000. Well, we look at this list and we see T8 doesn't contain a left zero semigroup of size 1000, but T9 does. So therefore the degree is 9. That's the smallest n containing a left zero semigroup of size 1000. All right. Similar things happen for right zero semigroups. In mind of the time, I'm probably going to skip over this a little bit, but we answer this by also looking at the kind of switched around question, given n, what's the biggest right zero subsemigroup? Well, here any right zero semigroup has elements with a common kernel. All right, so this time we've got the A's fixed, and we can choose idempotents just by picking any element from A1, any element from A2, etc. And so it turns out that the size of a big right zero semigroup with this kernel is given by the product of the sizes of these sets. This time it does depend on the sets, not just the number of sets. But what this is it's a product of R integers whose sum is actually n. Okay. It turns out that this is maximized when the integers are basically equal, or as equal as they could be, roughly equal to n over R. And then as we let R vary, this is maximized again when R is equal to 3. All right, so it turns out that the biggest right zero semigroup is basically you get n as a sum of as many 3s as you can, and whatever's left over, you have a couple of 2s maybe, and then you multiply all the 3s and 2s together, and that's the size there. So that's the numbers you get for rho n. Then we get the degree of a right zero semigroup by minimizing n such that rho n is greater than or equal to p. If we actually compare this to the lambda values, you can actually see that they're very different. So so the degree of a right zero semigroup is not the same as the degree of a left zero semigroup. And it might look like it would take a very long time to get the number 1000 in this top row, but in fact, things are roughly multiplying by 3 as you go, so you get there soon enough. All right, what about null semigroups? Well, this is sort of uncharted territory in terms of when we picked up this project, but we can answer it in the same kind of way. Given n, what's the biggest null semigroup we can find? So we want to find a null semigroup of Tn, subsemigroup, with a given 0. Now the 0 element is going to be an idempotent, so let's call it zeta, and let's imagine it looks like this. It's convenient to put the image point over to the left. And what we do is, for each of these triangles, we fix a subset of the z and make sure it contains the point from the image. Then we look at all the functions. It's written here in symbols, but basically all the functions that this fixed y guy, every element of that maps down to the x, and the rest of the z maps into the y. Okay, we look at all the functions of this form, and if you imagine composing this f with a g that does basically the same thing, well, everything goes into the y, and then when we do g, that all goes down to x. So the composition of any of 2 of these guys is going to be zeta. So these all form a null semigroup with 0 zeta. And it turns out that any null semigroup with 0 zeta is contained in one of these things for some carefully chosen sets y. So the biggest null semigroup is one of these sort of things. The size of n can be calculated fairly easily. The freedom we have is just deciding where these elements, where the other elements, say of Z1 are going to go. They can go anywhere into Y1. So you work it out and it gives you this formula here. So it turns out this size is sort of a bit complicated, but it's always maximized when there's only one element of one triangle. So just Z1 to the Z1, sorry, Y1 to the Z1 minus Y1. Z1 is just everything. So Z1 has size n, and if you write k for the size of Y1, this is just k to the n minus k. All right. So the biggest n has this form, and we just vary k and see what's the biggest thing we can get. So the biggest null semigroup is the maximum of k to the n minus k as k ranges over n. And if this seems vaguely familiar, it's because that's the same as lambda n from before. So that means, in fact, that the degree of a null semigroup of size p is the same as the degree of a left zero semigroup of size p. And apart from this just being so, we don't really have a deep understanding of why that should be the case. Okay, we calculated 2 things and got the same answer, rather than we sort of match them up in some way. Right, so I'll try and conclude by saying a few words about rectangular bands. This is the sort of the real interest of this talk. So what's the degree of a p by q rectangular band? We don't have to worry about p or q being 1, otherwise this would just be a left zero semigroup or a right zero. So the other thing to note is that because we have 2 parameters, we can't just say what's the biggest rectangular band in Tn and then turn this question around, because the biggest rectangular band might be a 1 by 1000 one, and that doesn't help you know if there's a 500 by 500 band in there. So the trick is that we're going to let beta pq be the degree of this thing. It doesn't seem like a big step, but it allows us to introduce a new parameter, r. So we're going to let beta r pq be the minimum n such that some set that now has an r in it contains a p by q rectangular band. That set is the set of all transformations of degree of rank r. Okay, it turns out that any rectangular band contained in Tn is going to have a common rank. This is another Green's relation trick. All right, and then beta of PQ is just the minimum over all of these beta R's. So somehow if we can answer this bigger problem, we can answer the original problem, and the bigger problem with the extra parameter is actually more convenient. So let's consider a P by Q rectangular band consisting of transformations of degree n, all of rank R. We're going to let I be the set of all images of all of these elements. Okay, and what we in fact have is a bunch of subsets all of size R, and therefore we can think of this as some kind of graph. Okay, in a graph you have edges which connect 2 points. In a hypergraph you have hyperedges which connect some points, might be 2 points, might be 5 points. In this case we've got a hypergraph with 6 vertices, and the hyperedges each connect 3 points. Okay. Then we let K be the set of all kernels of our elements of from our rectangular band. These are all partitions, each of which has R blocks. And the magic of this is that every kernel is a proper coloring of this graph. Proper coloring, we might remember from ordinary graphs, is where every edge connects colors, connects different colors. Well, here, every hyper edge has to have different colors on every vertex. So this is a proper coloring of this hypergraph here. Every edge has 3 different colors, different colored vertices. The number of colorings is P. The number of edges, hyperedges, is Q. So somehow all the parameters of our rectangular band get mixed together in this graph, and the elements of the band I won't go into too much detail, but they're described by the kernels and the images, like so. So the idea is that any rectangular band of rank R transformations of degree n leads to a very sort of symmetrical graph. Lots of edges, lots of colorings. And on the other hand, any hypergraph with such colorings leads to a set of idempotents that's P by Q, but the problem is it doesn't necessarily have to be a semigroup. It might just be a bunch of idempotents that you multiply them together and you don't get idempotents back. But the key thing is that if you can find such a set of idempotents, there's always one that gives you a nice rectangular band. So this lets us come up with a formula which is quite mysterious until you read the details, but it actually gives us a formula for beta R PQ, and then in turn for beta PQ itself. So I'll just conclude with some numbers. They don't sort of say much just by looking at them, but what's interesting, for example, is a 10 by 10 rectangular band can be embedded in T10. And if you go up to even bigger numbers, this is about as far as we went, a billion by billion rectangular band can be embedded in T64, which is much smaller than a billion. So as n increases, you can get bigger and bigger bands. But anyway, that's basically where I think I'll stop. So thanks very much for your attention.
Thank you, Professor James East. So let's have now a 5-minute break, and then the next session will be shared by Professor Pilippa Pattison. Thank you.
Okay, shall we start? Welcome back, everybody. It's my great pleasure to start with to introduce Paola Caterino, who's going to talk about revisiting some research work in a particular semigroup of transformations. Paola, over to you.
Okay, so I asked the organization to share my video because I have problem before. So the organization, some people from the organization informed me that the video is now okay to share. So please, can start. Okay, thank you.
Good morning for all participants in this conference. First of all, I would like to thank the organizing committee about the invitation sent to me in order to be one of the invited speakers of this conference. In particular, I express my gratitude to Melanija M.Mitrović. In the last few years, I did not study semigroups of transformation anymore. for several reasons and circumstances in my life. However, and because it was a topic of my PhD, I am currently thinking about continuing to investigate this area that gave me so much pleasure at that time. So it is not my intention to show anything new that I have done in this area, but rather to show some of the impact that some articles that support my PhD thesis have had and continue to have acceptance in scientific community interested in the study of transformation semigroups. So we are going to recall some research work in a particular semigroup of transformations. As we have mentioned before, in this presentation, it is my intention to remember and make known some research work related to a particular case of two semigroups of transformation on a finite chain. The semigroup of orientation preserving and the semigroup of orientation reversing transformation on the chain. I finished my PhD thesis in the University of Essex, and my supervisor was Professor Peter Evans, and the main examiner it was Professor John Howick, a great mathematician from the University of St. Andrews, to whom I pay tribute now. In this slide, we present the three main papers included in my work that have a very good acceptance in scientific community, especially the first two papers where a new semigroup of full transformation were introduced and studied. Here we present some notation, some usual notations about included in this topic. Tx, it will be the full transformation semigroup on a set X. Xn, it will be the finite chain of the first n elements of natural numbers with usual order. Tn, it will be the full transformation semigroup on the chain Xn. So here we have two examples of mappings in Tn. Mapping A, which is a cycle of order n, and the mapping gamma. Also, the notation Zn, it will be the cyclic group of order n, which is generated by the cycle A, and Dn, it will be the dihedral group of order 2n, which is generated by the above mappings A and gamma. I use PTX for the partial full transformation semigroup on a set X, and if you consider Xn instead of X, I use the notation PTN for the same partial full transformation semigroup. So we are going to present here the definition of order preserving mapping on a Xn, and we say that alpha is an order preserving mapping on Xn if whenever we have I less than or equal j in the chain Xn, then the image by alpha satisfy this condition. I alpha is less than or equal j alpha. Therefore, if alpha is an order preserving mapping, then the image under alpha satisfy this condition. And we are going to use by ON the notation represent the semigroup of all order preserving mappings on Xn. Here on the left side we have the definition of a cyclic sequence. So we say that the sequence of T elements from the chain Xn is cyclic or has a clockwise orientation if there exists no more than one subscript I such that AI is greater than AI plus 1. The addition considered here is module T. So we have here two examples of a sequence of elements from the chain X5 and X3. The sequence A is cyclic because 5 is the unique element, unique value of this sequence that is greater than the next one. And B is not cyclic because we have more than one value in this condition. So we have 3, the first 3 is greater than the next one, and also the other 3 is also greater than the next one. So we have more than one. On the left side, we present the definition of anti-cyclic sequence, and we say that a sequence of T elements from Xn is anti-cyclic or has anti-clockwise orientation if there exists no more than one subscript I such that AI is less than AI plus 1. Once more, the addition considered here is module T. Here we have two examples of sequence. A is an anticyclic sequence and B is not anticyclic sequence. So the characterization of a sequence should be cyclic or anticyclic is the following. A finite sequence of T elements of Xn is cyclic or anticyclic if and only if there exists an I from xt such that these conditions are satisfied, and I is unique unless the sequence is constant. So we have here some examples of cyclic sequence, anticyclic sequence, and the last one is both cyclic and anticyclic sequence. Note that the first one is cyclic because I is equal 4 is the unique value of I such that AI is greater than AI plus 1. I is equal 4 corresponds to the value 5 in the sequence. On the right side, A is anticyclic sequence because 5 is the unique value of AI such that AI is less than AI plus 1. And the last one is both because this sequence has two values. A nice picture that we can draw in order to represent an orientation preserving mapping is that picture that I have on the right side. On the left side, we have the definition of orientation preserving mapping. So we say that alpha is an orientation preserving mapping in this chain Xn if the sequence of image under alpha is cyclic. So on the picture, this means that when we draw the arcs between the domain which is in the bigger cycle and the codomain which is in the not bigger, the other cycle, if we can draw the arcs without crossing, so we have an orientation preserving map. So we say that alpha is an orientation preserving mapping if and only if the arcs in the picture can be drawn without crossings. This is what's happened in the first image, and this is not what's happened in the other image. So we have here two examples of two mappings, which are orientation preserving mappings and the respective pictures. So we can see that we don't have crossings in the arcs. We draw these arcs without crossing. In the particular case of the last one is also an order preserving mapping. Okay? Here we have an example of a mapping which is not an orientation preserving mapping. Note that when we draw these arcs between the domain and the respective image, we have a cross there between two of arcs, these arcs. So we have the definition of orientation reversing. And we say that a mapping alpha is an orientation reversing in XN if the sequence of image under alpha is anti-cyclic. So the notation that we are going to use, and in my thesis I introduced these two semigroups. The first one, it was OPN, which means that the submonoid of TN consists of all orientation preserving mappings in XN. And the second semigroup, it was PN, which is the union of all orientation preserving mappings and all orientation reversing mappings. Note that ORN itself is not a submonoid, because the product, the composition of two orientation reversing mappings is not an orientation reversing mapping. Also, note that the semigroup ON, which is the semigroup of all order preserving mapping, is a particular case, is a subset of OPN. Also, this remark, interesting remark, for n is equal 1, we have T1 coincides with OP1 and coincides with P1. For n is equal 2, T2 coincides with OP2 and coincides with P2. For n is equal 3, is valid that T3 coincides with P3, and for n greater or equal 4, this is not valid. Now we present some interesting results that are stated in my thesis. One of these interesting results is that OPN can be characterized by this product, Zn with ON, which means that any orientation preserving mapping can be written as a product of an element of the cyclic group of order n and an order preserving mapping. Also, another interesting result is that any kernel class of an orientation preserving mapping is convex. And also, this semigroup is a regular semigroup. So, we have here the characterizations of the Green's relations in this semigroup OPN. Another interesting results that we can find in my thesis, some of them are combinatorial results, is the following. The product of an orientation preserving mapping with an orientation reversing mapping in both sides is always an orientation reversing mapping. The product of two orientation reversing mappings is an orientation preserving mapping. Also, as we said before, OPN is a regular semigroup, and also PN is a regular semigroup. Remember, PN is the semigroup of all orientation preserving mappings and also all orientation reversing mappings, or all orientation reversing mappings. Also, the idempotence of PN coincides with the idempotence of OPN. And now for combinatorial results, we have the number, the cardinality of OPN, the cardinality of idempotence in ON, and the cardinality of the idempotence in OPN, and the cardinality of PN. Interesting that the cardinality of OPN is also related with Fibonacci numbers, and the sum of these two Fibonacci numbers can be also related with Lucas numbers. Another study in my PhD thesis, it was the digraph, the functional digraph of this kind of mappings. So we present here, we recall here some of these results about the digraph of an orientation preserving mapping. And the first one says that the digraph of an orientation preserving map cannot have a non-trivial cycle and a fixed point at the same time. Also, the digraph of an orientation preserving map cannot have two cycles of different length. Also, if you have an orientation preserving mapping with fixed points, then the graph of alpha is a forest, and each component C associated with a fixed point of alpha as an interval. Also, if given a functional digraph, G on endpoints, all of whose cycles are the same order M, if you have in this condition, then there exists an orientation preserving mapping with the digraph G. Here we present two examples about the digraph and the corresponding orientation preserving mapping. In the first case, we have one component and one cycle, and we have the corresponding orientation preserving mapping alpha. The second one, they have two components and the corresponding orientation preserving mapping is below. Now I'm going to show the impact of some of these semigroups. First one, in this slide, on the top of this slide, we can see the number of citations that one of the papers published on journal Semigroup Forum has from Google Scholar. This is from Google Scholar, 19 citations. The paper is, as we said, published in Semigroup Forum in 1994. The same paper from Crossref, we have 26 citations for the same paper. Also, the same paper from Zentralblad Maths, we have 24 citations in documents and 2 in reviews. From now on, we present several new papers with works related with these two semigroups of transformations. Here, in 2000, Professor Vitor Hugo Fernandes, from my work, introduced a new semigroups of transformation. It was the monoid of all injective orientation preserving partial transformation on a finite chain. In 2001, the same colleague, from once more my work, a new relationship between the semigroup of orientation preserving mappings and other semigroups of transformation is established here. In 2005, also Vitor Hugo Fernandes, Gracinda Gomes and Manuel Jesus studied the presentation of some monoids of partial transformation on a finite chain, and also they studied the partial transformation of orientation preserving mapping and also orientation preserving mapping or reversing orientation mapping. In 2018, Zhao studied the locally maximal idempotent generating subsemigroups of singular orientation preserving transformation semigroups. This colleague, Zhao, introduced a new semigroup of orientation preserving mappings, which is called by singular orientation preserving mappings. In 2006, Inessa Levy and John Mitchell also study on rank properties of endomorphisms of finite circular orders. And they say in the abstract that in particular here is studied a semigroup of all mappings generated by orientation preserving mappings whose kernels are of a fixed type R, where two partitions are said to be the same type if they have the same size and the numbers of class of each size. In 2009, also ZOO studied a classification of maximal idempotent generated subsemigroups of singular orientation preserving transformation semigroups. Once more, this colleague studied a new property of this new semigroup, which is the semigroup of singular orientation preserving mappings. In 2009, Vitor Hugo Fernandes, Gracinda Gomes, and Manuel Jesus also studied the congruence on monoids of transformation preserving the orientation on a finite chain. In 2011, once more, Vitor Hugo Fernandes, now with another colleague, Teresa Quinteiro, studied the bilateral semi-direct product decompositions of transformation monoids. And once more, they study these semigroups of orientation preserving mappings and the orientation orientation reversing mappings. Also, today. 2011, another study from ZOO about the classification of maximal idempotent generated subsemigroups of finite orientation preserved singular partial transformation semigroups. Now is a partial, not a full transformation semigroups. Also in 2010, ZOO studied the maximal regular subsemibands of the orientation preserving mappings, which are singular. 2014, Vitor Hugo studied once more the monoids of transformation that preserve uniform partitioning. In 2016, once more, Vitor Hugo and more colleagues studied semigroups on orientation preserving transformation with a restricted range. 2015, the ranks of ideals in various transformation monoids, in particular these two monoids were studied by ZOO and Vitor Hugo Fernandes. In 2013, locally maximal idempotent generated subsemigroups of finite orientation preserving singular partial transformation semigroups are described. In 2018, on the nilpotent ranks of the principal factors of orientation preserving transformation semigroups were studied by ZOO. Once more, ZOO and more colleagues studied the maximal regular subsemibands of the finite order preserving partial transformation semigroups. 2019, Peter Higgins, my supervisor, decided to restudy again this semigroup, and he published in Semigroup Forum the involution matchings, the semigroup of orientation preserving and orientation reversing mappings, and inverse covers of the full transformation semigroups. In 2021, Dimitrova and Pattison also study the relative ranks on the semigroup of orientation preserving transformation on infinite chain with restricted range. And finally, I present here, which was in 2020, also Peter Higgins and my colleague Alexei, my colleague in PhD also, Alexei Vernisky, study a new formulation of the semigroup of orientation preserving and orientation reversing methods. So, many research have been interested in semigroup of orientation preserving mappings until now. From the introduction of the new semigroups of this type to the study of algebraic properties of these and other semigroups of transformation, we can say that this topic has contributed to the development of the study of semigroups, in particular of finite semigroups of transformations. Thank you very much for your attention. Thank you.
Thank you so much, Paula. That was wonderful. We're now going to move to the talk. We're now going to move to the talk by Mahouton on decompositions of an Abel-Grassmann's groupoid. Welcome, Mahouton.
Thank you for inviting me, for introducing me. Let me share my presentation. I hope that you can see my presentation now. I shared it. Okay.
We can. It might be better on full screen.
I'm very much thankful to Professor Melanija for inviting me to this conference and giving me a chance to present my work. The title of my presentation is on Abel-Grassmann's groupoids and the decomposition of Abel-Grassmann's groupoids. So first, let me introduce, this is a new structure. Many people must be unaware of the structure. So first, let me introduce the structure. This is an algebraic structure with one operation and satisfying a left invertive law. This is not a semigroup. This is a mid structure between a groupoid and a commutative semigroup. I will discuss these. I wrote the abstract of the paper here. I will give the full detail of this abstract. So this is, as I said, this is a new structure introduced in 1972, and the people in Pakistan, they call it left almost semigroup. This is not an exact semigroup, so they use the name left almost semigroups. And Professor Stepanovic, they use the name of Abel-Grassmann's groupoid. Here I give the citation of Professor Stepanovic. He called it Abel-Grassmann's groupoid, and shortly we call it AG groupoid. So this is a groupoid satisfying a left invertive law. This is what we call left invertive law, which was introduced by M.A. Kazim and M. Nasiruddin, while M. Nasiruddin was working on his PhD thesis. They were actually working on ternary semigroups, and that they saw this law. This is a commutative law in ternary operations. A, B, C is equal to CBA. So they put the bracket on the left side, AB into C is equal to CB into A. If this law holds for all A, B, C, and S, where S is a groupoid, then S is called a left almost semigroup, and we abbreviated as LA semigroup, and some professors call it Abel-Grassmann groupoids or AG groupoid. As I said, this is what we call it in Pakistan, that left almost semigroup. I give the citation of Professor Kaisar Mushtaq, who did PhD from Oxford. He was my advisor, and now he is retired. And the same structure is also called left inverted groupoid by Philip Holgate. I read his paper. He was working, he's actually famous on working on non-associative algebraic structures which have genetic realization, that has genetic applications. So he also wrote a paper and called it left inverted groupoid, because this is also a non-associative structure. So he also wrote just one paper and did some initial basic work. As I said, this is a mid structure between a groupoid and a commutative semigroup. This is in between a commutative semigroup and a groupoid, and very near to a commutative semigroup. Let me explain further. If S is an AG groupoid, then for 4 element, this law also holds an S. AB into CD is equal to AC into BD. This automatically holds with the left inverted law. If S is an AG groupoid, then automatically this is this law holds in it, and this law is called medial law. And many of you may be aware of the several groupoids like medial groupoids, paramedial groupoids. So if S is an AG groupoid, then this automatically satisfies the medial law. So an AG groupoid is also a medial groupoid. And this is an example with 3 elements. This is the example of an AG groupoid. Here it is necessary to know that like a semigroup, we can adjoin an identity, but in an AG groupoid, we cannot adjoin an identity. It doesn't contain even an identity, but it can contain a left identity. And if the left if it contains the left identity, then the left identity is unique. And it doesn't contain the right identity. If it contains the right identity, then it becomes a commutative semigroup. So it doesn't contain a right identity, but it may or may not contain a left identity. So here, this is the example of an AG groupoid with the left identity 3. As I said that it doesn't contain a left identity, sometimes it may contain, and if it contains a left identity, then this law is also holds an S. AB into CD is equal to DB, CA. And this law is known as paramedial law. So if an AG groupoid contains a left identity, then this is also paramedial groupoid. And if it contains a left identity, then this law also holds an S. A into BC equal to B into AC for all A, B, C belongs to S. And why we study this AG groupoid? You see, as this is a mid structure between a groupoid and a commutative semigroup, this is non-associative basically. And if you see, this law is hold A square B square equal to B square A square. This law holds in a commutative semigroup or a commutative group. But if an AG groupoid contains a left identity, then this law also holds in S with left identity. So see, this is the structure is mostly work like a commutative semigroup, while this is the generalization of a commutative semigroup. And commutative law doesn't hold an AG groupoid because commutativity gives associativity. So since this is a non-associative structure, so we avoid commutativity because commutativity gives associativity. But with left identity, it's still a non-associative structure, and it satisfies this law, which generally holds in a commutative group or in a semigroup. And we can see we cannot define powers of an element in AG groupoid because it is not associative, and powers of an element we can define by associativity. So if we introduce the local associativity, by local associativity mean if this A square A is equal to AA square, the associativity holds just for particular elements for all A and S, then S is called locally associative AG groupoid. This is not still not associative, but this is locally associative. And if we introduce the local associativity in AG groupoid, then we can define powers of an element. And if we see the powers of an element, if we define powers of an element, and if S is an AG groupoid with left identity, then this law holds in S. A power n, B power n is equal to Bm an. And this holds for all Mn greater than 2. Mn cannot be equal to 1 because we take 1, then this is commutativity. Commutativity generally doesn't hold in it. So this law holds for all Mn greater than 2. And here I want to mention that if, there is a famous paper known as a semigroup satisfying AB power m is equal to am bm for all m. This paper is published in semigroup forum. I will show you the paper at the end. So semigroup satisfying that identity, this identity is the generalized identity. And this holds in a non-associative algebraic structure locally associative AG groupoid, but it must contain a left identity. Without left identity, it doesn't hold this, this identity. And here I also discuss AG star groupoid. What do we mean by AG star groupoid? A groupoid, an AG groupoid satisfying this law, AB into C equal to B into C. If this law holds for all A, B, C in S, then the AG groupoid is called AG star groupoid. So I also discuss some properties of the AG star groupoids here. The AG star groupoid is also a non-associative algebraic structure. This is known by AG star. This name is given by Professor Stevanovic in his paper. And automatically, this law is also held because of the left invertive law. And this is the famous identity introduced by, excuse me. This is the famous identity introduced by Professor Stevanovic in his paper. If S is an AG star groupoid, then S square is commutative. Generally, this law holds. This law 5 holds in AG star groupoid. This is the most beautiful identity. I can say that this is, I like this identity, where this pi is means any permutation and the set 1, 2, 3, 4. And this simply we can say that if S is equal to S square, then S is a commutative semigroup. So we can deduce that we cannot even take a left identity in AG star groupoid. Because if we take a left identity in AG star groupoid, then S is equal to S square, and then this S is a commutative semigroup. And we have to avoid the commutativity and associativity because this is a non-associative structure generally. So many characteristics of the non-associative AG groupoid and AG star groupoid is similar like a commutative semigroup. And the law 5, easily we can see this. Excuse me. And it is easy to see that if we define local associativity, or if we take an AG star groupoid, which I already defined above, then we can define powers of an element, and if we use that power of an element, then we can, like in semigroup, we can define a relation rho like this: A is rho related to B, if and only if ABN is equal to Bn plus 1 and Ban is equal to N plus 1. This is this relation is already discussed by Pilippa and Preston in their book. But the structure is non-associative, so we can decompose AG groupoid using this relation rho. And this is another relation, sigma, defined like this: A is sigma related to B, Fn only this equation, these two equations, or this is quite different from the previous relation rho, sigma. Sigma and rho, these are quite different. And this is the definition of separative congruence. We will use it. Here, both the relations, I will discuss the sigma and rho. They have a common relation. We can decompose a structure using sigma and rho, but the structure with some power of particular power of n, the structures are isomorphic. See, if we take S as an AG star groupoid, then rho is commutative. A, B is rho related to BA for all A, B, and S. Similarly, the sigma is commutative. These are the theorems already proved. I will show in references, these papers are already published, but if you can see this lemma and this theorem, these two quotient structure, S vector rho and S vector sigma, these are isomorphic in energy star groupoid. And for Mn equal to 1, of course, these are quite different. Both the structures are quite different, but both are isomorphic for Mn greater than or equal to 2. Generally, Sxs is not equal to Sxs. So if you define the operations using this and this, and these are quite different relations. So I define a relation gamma. A is a gamma related to B, if and only if Bn belongs to SAS and An belongs to S into Bs. The bracket matters here because the structure is non-associative, so we have to put bracket either on the left side or on the right side. And this is the relation delta I define. A is delta related to B if and only if these two conditions hold. Since the structure is non-associative, but both the relations are equivalent. Sigma and gamma, these are equivalent in an AG star groupoid S. And here is another decomposition, similarity decomposition. These laws are already discussed. Pyramidal law. If an AG groupoid contains a left identity, then of course S is equal to S square. And as I said, that the bracket matters here because the structure is non-associative. So we can define powers of an element like this. By this I mean A cube equal to A square into A, and so on. A4 is equal to A cube into A. The bracket is on the left side. See, this is A cube, they highlighted, and this is A4 and so on. So the powers we can define particularly like this. Here is another example of an AG groupoid. These equations are already proved in the thesis of Professor Sarvakrama, and this is a PhD thesis. I use these equations. It is easy to see that this law holds in S, where S is simply a non-associative structure, a G groupoid containing a left identity. Here I define another relation like this: X is eta related to Y, if and only if X A N belongs to Y A into S and Y A N belongs to X A into S. And I will decompose the structure using this relation. As I already discussed, that A square B square is equal to B square A square in an edge groupoid with left identity. And the eta I define is a similatous congruence on S. Similarly, eta is a separative congruence on S. So here is the final result that S vector eta, this quotient structure, is a similated separative homomorphic image of S. This actually proved by Clifford and Preston in their book for semigroups, but here we proved it for the non-associative structure, namely AG groupoid. These are the references I use. As I said, this is the paper of Professor Holgate. He worked on non-associative algebraic structures, and this is also with two operations. Of course, he is working on those non-associative structures which have genetic realization, which has genetic applications in genetics. So he also worked on this, and he discussed few basic properties of this AG groupoid. And he named it the groupoid satisfying simple invertive law. The law, we named it left invertive law, and he called it a simple invertive law. And this is the PhD thesis of Professor Sarvakrama. Last year he was retired, and last year he died. And this was the first paper on this non-associative algebraic structure in 1972. I met this guy, the son of this guy, who is now American. He is living in America, M.N.Hounkonnou. His son is living in America. He is a professor. And this is the paper of Professor Mushtaq and his student. This is published in Semigroup Forum. Decomposition of locally associative LS semigroup. LS semigroup, this is left almost semigroup. Here in Pakistan, they call it left almost semigroup. And Professor Mushtaq was my advisor. He is now retired. And this is the paper published in my paper with my supervisor, published in Algebra Colloquium. And this is me again, the paper on the same structure published in Acta Mathematica Sinicum, which is very much related to this work. And similarly, this is the decomposition of AG star groupoid published in Kozai groups and related system. And this is the paper of Professor Stemeanovic. I really like the work of Professor Stemeanovic. I studied in my PhD thesis. I reviewed many of his papers. And with this, that's the end. Thank you. And if you have any question, any comment, I'm here. Most welcome, please.
Thank you so much, Manoj, for that very interesting talk. I think we're going to have a short break, but I hope we'll get to questions later on in the discussion section. So let's go to a break, and I think when we come back, Norbert will be in the chair. Thank you very much.
Again, thank you very much to the organizers. It's a great privilege and honor to be here. I never expected to be part of an algebra conference. This will find its way into our institute newsletter. This is something that doesn't happen very often in Wrocław, Poland. So again, very proud. Thank you especially to Professor M.N.Hounkonnou for reading my book, How We Understand Mathematics 2018, which is part of the Mathematics in Mind series of Professor Marcel Denesi. I think we all worry. I remember Professor Boyd yesterday expressing his worry about no one reading his books. I'm sure it's not the case. It's great pleasure to know that that sometimes our book are read. As I was taught in teachers training, I should tell the audience first what it's going to be about, then tell it, and then tell it again, tell them what I've just said. So I'll just tell you that it will be about metaphors in mathematics, and I will be trying to answer the question of whether the world is mathematical or whether perhaps mathematics is of this world. I will explain everything in a moment. Let's move on to the next slide. Yeah, right, this is part of my abstract Apollo landing as an example of how wonderful mathematics is and what it can do. But of course, there are so many other such examples. I remember at the opening of the conference, Professor M.N.Hounkonnou mentioning the symmetries in the natural world. And by the way, thank you, Professor Hounkonnou. I never expected my book to be quoted at the very beginning of this wonderful conference. It was probably the proudest moment of my life. So many were asking, or are still asking, is God a mathematician? Is the world mathematically rational? Is mathematics there, ready to be discovered by anybody, not only by humans, but by aliens from outer space? There is this anecdote about Gauss, probably not true, in the 1820s, that he wanted to construct a great Pythagorean right triangle in the Siberian tundra for the aliens from the moon and from Mars to see it, and to know to discover mathematics as it is, ready to be discovered by any species, not only by humans. The same sentiment was expressed by 1963 Nobel laureate Eugene Wigner, a physicist who ended his essay called The Unreasonable Effectiveness of Mathematics in Natural Science in the following way. I will read it aloud. He said, "The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research that will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning." So I'm going to talk a little bit about this bafflement. And Wigner really knew what he was speaking of, because he got his Nobel Prize for discovering and applying fundamental symmetry principles to the world of elementary particles. So moving on, a possible answer to Wigner's puzzle, is God a mathematician? Is the world mathematically rational? We may try to say that perhaps she is. We don't know yet, but we can posit that perhaps it's the other way around, which means mathematics is of this world, and that's why it works in this world. And here are two points, two more precise points for this answer. Mathematics is of this world because the dynamic scenarios or series of timed events that provide the wealth of meaning to mathematical concepts are of this world, i.e. are convergent with how we experience and describe it, including by means of physics, biology, sociology, arts, etc., etc. And additionally, the said wealth of meaning, or polysemy, as we call it in linguistics, we have detected, or well, I have detected in this presentation, I will detect, I will try to show you, of fundamental mathematical notions may account for the incredible versatility of mathematics and the fact that it never dries up, always works in a wonderful way. So there will be more examples to follow, and I hope more precise, but just to give you a general idea, let's consider moving stones for a moment. It has certain properties we are all aware of, as for example, if the stone is a microscopic object, it cannot be put in two places at once, and if you move the stone again, the combination or the composition, right, of those two moves is also a move, and you can always take the stone back and then you get a zero move. What we have here is a group, of course. A set of stone moves is a group. But let's get to more specifically to the point. I want to focus for a moment on the concept of mathematical mapping. The word mapping, I think, appeared in every previous presentation today at least several times, tens of times, probably hundreds of times in the entire conference. And this is why perhaps Herstein, the author of the algebra, very well-known and much loved classic algebra handbook for sophomores at Cornell, calls it probably the single most important and universal notion that runs through all mathematics. I'm sorry, I just have to, I need to be aware of the time. Yes, what I want to show you is that algebra handbooks prompt the reader to understand mathematical mapping or function through a number of simple scenarios involving people or actors doing things. So here is what Herstein says. He gives this formal definition, sometimes called a definition by graph, which we all, of course, you all, especially the real mathematicians, know very well, sometimes called definition of piano. So I'll just read it. If S and T are non-empty sets, then the mapping from S to T is a subset or M of the product of S and T, or a Cartesian product, such as for every S in S, there is a unique T in T, such as the ordered pair ST is in M. And then Herstein says something striking. He says, this definition serves to make the concept of a mapping precise for us, but we shall almost never use it in this form. Instead, we do prefer to think of a mapping as a rule which associates with any element S, some element S in T, a rule which associates. He uses a verb. The mapping is no longer static. a set of ordered pairs, but it's an action performed by somebody, perhaps a matchmaker who connects people into pairs. So there is some reason Herstein prefers to avoid this precise definition, as he calls it. And the second book I'm going to quote is first year calculus. The authors, I think, are Dougherty and I forgot the other. I will remember in a moment. Anyway, they say popular handbook. They say it's probably the only calculus handbook meant to be read or even curled up and read. And they say they give the same definition, the formal definition, and then they say, while we mention it, we will not use it within the rest of the text because it de-emphasizes functions as actions or processes taking inputs and deterministically returning outputs. So what we have here is what Mark Turner calls small spatial stories, simple scenarios where there are actors performing actions. In the first, we have a rule or a matchmaker, let's call it that. And in the second, we have black box, or we can call it a grinder. We put something in, something else comes out. So far, we have those two scenarios prompted by algebra and calculus handbooks. But this is not the end of it. Herstein says that at one point, introducing the mapping, he says that mapping takes every it's called quadratic function. It's not easy for me to remember because I studied physics and mathematics in Polish, but okay. And he says that this particular mapping takes every real number onto its square. So we have mapping in this scenario. Mapping is a sort of a carrier, someone who moves objects from one place to another. So we have three scenarios so far. Let's concentrate only on the colored text because I'm afraid I will run out of time. We have the matchmaker, the black box or the grinder, and the carrier. Those three scenarios can be found in the two algebra handbooks mentioned, and they can be diagrammed in this way. We have a grinder on the left, and the right diagram, very typical, can represent both matchmaking and carrying. So those three scenarios, moving very quickly on. And yes, let's focus for a moment on this ordered pair that appears in the precise definition. Usually a primitive notion, which means not defined. Herstein, Dougherty, Bourbaki, Hausdorff tried to define it, but I will not have, very interesting, but I will not have time to talk about it. Usually not defined, but if we consider it, if we think about what makes a pair order, well, we have to know which element is left, which element is right, or which is first, which is second. So when we think of it very hard, we come to a realization, and I move quickly to the bottom of the screen, that an ordered pair is a one-to-one mapping from the set of indexes, like 1, 2, or left, right, etc., to the elements of the pair, or the other way around. It would not make a difference because it's one-to-one, but we can't say this out loud. And I am sure I don't have to, I will say it out loud in a moment, but I'm sure you already know why we cannot admit for this precise definition that an ordered pair is a mapping. Because then, of course, the rigorous definition of a mapping would be circular. A mapping would be defined as a set of mapping. We cannot have that. So let's leave it as a primitive notion. But let's look at those already mentioned dynamic scenarios. Perhaps they have the same fault. Perhaps they also, there is also a problem there with ordered pairs, because when you think of the carrier, quadratic function that carries object from one place to another, it also creates ordered pairs like 2, 4, 3, 9, 4, 16, etc., etc. So how do we know in those dynamic scenarios, little small spatial stories, that the pairs are ordered? And the answer to this question is they are ordered because they occupy different roles in the scenarios. They are perfectly or naturally ordered. For example, X is the number that is being carried on, and Y is the spot on which the carried number is placed, etc., etc. X is the element, the meat that comes into the grinder, and Y is what comes out of the grinder. And also because those scenarios are timed, they are dynamic, the pairs are ordered temporarily. So the dynamic scenarios that we are prompted to use in algebra handbooks solve this problem of circularity of the so-called rigorous definition, which is so studiously avoided by the great authors, algebra teachers or calculus teachers. So let's look again at those different way of thinking about a mapping. We have a set of ordered pairs, which is static and perhaps circular, could be the matchmaker, the black box, and the carrier, and there are more. So graph could be considered one, because when we use a graph, we have to move from X, turn at the graph to the left, etc., or to the right. So this is another dynamic scenarios, which I called the hiker. Also, if we read Dougherty, we can read that the function in the above example can be described as a process by which the input is first square and then the result is added to 1. And I called this scenario the chef who takes the ingredients and processes according to formula or recipe. So what we have, I have to be very fast now. What we have here is 6 dynamic scenarios. And the question, of course, is which is better? Which is better? And we find the answer in Dougherty. And let's just look at the blue text here, who says it's best to consider functions in all these ways. And now there won't be almost no linguistics, but just one little bit. So the question is at the bottom of the screen, are we, all of us Homo sapiens? They say, Lakoff and Nunes say that mathematicians are also Homo sapiens. I don't believe them. I think they are demigods, yes, but apparently they are also Homo sapiens. Are we understanding, are we capable of understanding one rigorously defined concept in so many ways at once? And now I am on a safe linguistic ground, and I will direct you to any dictionary to show you, for example, those 2 meanings of the word head. So one meaning of the word head is the upper part of the human body, and the other one is chief, principal, leading, or main. And those meanings are connected through metaphor. And this is how most meanings are connected in dictionaries. Of course, there are also other, there is blending, which is a more general system notion of metaphor, which I don't have time to go into. But let me just say this, and I'm reading here at the bottom of the screen that we routinely combine different story scenarios to create new meanings. So, and I don't have time to ask the audience, but I am sure if I did have time and asked you to combine the meanings of, let's say, set of ordered pairs and matchmakers, you would immediately say, well, those are very easy to combine, because you can imagine that a matchmaker in her notebook has a set of ordered pairs. Or can you combine, say, carrier and hiker? Of course you can. Hiker just goes and carries at the same time, not only hikes, but also takes a parcel for somebody to have. And the black box and matchmakers could also easily be combined. And this is what we do. This is what we humans do all the time. We blend concepts, and we do it all the time effortlessly and usually unconsciously. And now, almost finishing, how many 2-element subsets are there of a 6-element set? I'm sure there are people in the audience who could easily solve this puzzle, but of course, you know that there are 15 without repetitions. If we add the 6 original unblended meanings, it gives us 21 meanings of mathematical mapping, but of course we can have many more. So this is what I was talking about when I was saying that those dynamic scenarios give mathematical concepts a wealth of meaning. So very quickly to summary here, I hope we have demonstrated how simple the dynamic scenarios or small spatial stories allow through the process of conceptual integration or metaphor connecting stories for multiple ways of constructing the meaning of mathematical mapping. Analyzed fragments of 2 popular academic handbooks of mathematics, algebra and calculus, to show that the authors prompt for the use of small spatial stories, which we called variously Matchmaker, Black Box, Carrier, Hiker, Chef, etc. And I hope we have also demonstrated, or I have demonstrated, standing on the shoulders of giants, of course. I hope I have time to mention them very quickly, that those dynamic scenarios are not optional. They are like the flying buttresses to the beautiful cathedral of mathematics. They need to be there, otherwise it would fall down. For example, the rigorous definition of the mapping could be called circular. All right, this is just repeating what was already said, so I can say that this presentation has just crossed the finish line. Very quickly, the bibliography, the very first place, Professor Alexander already mentioned by Professor Danesi, I think also part of his book series. I don't have any more time, do I? No, thank you very much. That's it.
Thank you, Professor Wozniak, for your nice talk.
Thank you.
I hope everyone enjoys it.
Also too.
Let's now invite Professor Ronald Braiger to give his talk on conflicts as networks of event orderings.
Hello, my name is Ronald Braiger. My co-author and I thank you for your kind invitation to join you in this international conference, and we are privileged to do so. In the lower right corner of this slide is the Social Sciences building where we work at the University of Arizona. The talk is a further elaboration of work that appears in our published paper that I will be glad to make available on request, and is available also through this link. There has been a long tradition within network studies of seeking to exploit variable-centered approaches, such as surveys, as data for network analysis. I might just mention the names of Sorokin, Laumann, Blau, McPherson, and Burt. In this quote from 1981, Ronald Burt envisions connections between the usual concept of an actor's network position as embedded within webs of social relations, and what Burt refers to as combinations of attributes defining statuses in social structure. Burt put forward the notion that a network based on variables or attributes might serve as an ersatz or substitute for a social network. A key contribution to the study of narrative networks is the research of Peter Abel. In Abel's approach, narratives are conceived as directed graphs such that nodes are states of the world and arcs are events or causes. In our approach, nodes are variables or events, and the arcs are relations of precedence. There is a separate network and a separate narrative for each case. Our data come from a RAND Corporation study of 30 insurgencies worldwide. The RAND research combined 30 detailed case studies with systematic coding of event and attribute data. All the data we use are available to all researchers by means of the website at RAND, which is given at the bottom of this slide. This article in the academic research literature was also contributed by the RAND researchers. The scope of the RAND study was 30 insurgencies worldwide that were most recently begun and that had been terminated by the year 2008. 6 continents were represented among these cases. Because insurgencies are not homogeneous across time, the RAND researchers divided each case into phases or periods. There were 2 to 5 phases for each of the 30 cases, for a total of 86 periods. Like everything else about the study of insurgency and of social phenomena in general, subjective decisions cannot be avoided. The case analysts declared a new phase when they recognized a significant shift in the approach of the government or counterinsurgent or COIN forces, or a different approach on the part of the insurgents in the conflict, or thirdly, because of some exogenous conditions of the case, for example, the intervention of a foreign military. Narrative reports were provided for each phase of each case, and these comprise a 350-page volume, which is available to all researchers at the URL I gave previously. Most important for our purposes, 75 variables were defined for the study, and each variable was coded present or absent for each of the 86 phases in all across the 30 cases of insurgency. Here's an example from the 3 phases of the Algerian case. This is for the years 1992 to 2004. Our own research begins here with our puzzlement about the nature of the 75 variables, 3 of which are illustrated on this slide. These are certainly not variables in the ordinary sense of the word. They strike us more as researchers' claims about actions, activities, or events, that is, as potential constituents of narratives. We began our research highly puzzled about the meaning of these variables and their relation to one another. What, for example, is the difference, if any, between, for example, V2, the government or counterinsurgent forces were perceived as not worse than the insurgents, and V38, the population wanted the government forces to win? Does expanding secure areas, V4, lead to more favorable perceptions, V2? Or perhaps it works the other way around? Or perhaps these variables accompany each other? And how do the relations differ by types of case? We had no answers to any of these puzzles, and we were interested in using the data to reconstruct the mental map that the RAND researchers might have used or evolved in order to understand these questions that are at the heart of how insurgencies unfold. So here, for example, is a portion of the 75 variables for the case of Algeria. As you can see by the arrow, we implement our notion of the precedent of events. So we would say here that the government force is not perceived as worse than the insurgents precedes and the establishment or expansion of secure areas. Here are some of the same 75 variables for the case of Senegal. So again, we employ our notion of precedence. So the red arrows define precedence relations. So here, for example, the government provides services and subsequently there's a perception of security in areas claimed or controlled by the government. And then there are chains of precedent. So the government provides services, they're not perceived as worse. There are increased perceptions of security, and it's these that form the heart of our analysis. What I'm going to present today is the first analysis of the phased data. The original authors ignored all the data on timing. They defined a single crucial phase for each of the 30 cases. And in their quantitative analysis, the qualitative case studies were highly attuned to narrative, but in the second volume of their reports, in their quantitative studies, they analyzed only what they called the single phase, what they referred to as the crucial phase of each of the cases. We're going to look at all of them, and we're going to pay attention to sequencing. Here is an example of precedence relations among events in one of the 30 cases. The Taliban government, which came to power in 1996, and the insurgents, including ethnic minorities, predominantly in the north of the country, with the insurgents buttressed by the invasion of a foreign military led by the US following the events of September the 11th, 2001. In the diagram, the precedence relations constitute a partial order as represented by the Hasse diagram. Events are clustered, as in the second row of the diagram, if they have the same parents, the same children, and are all connected all to all. This is the same diagram with some of the variables named. I will make some substantive comments, but first I'll introduce our procedure for comparing event orderings across multiple cases of insurgency. This just introduces the concept of a Hasse ordering to represent precedence and transitive features of precedence. To compare two case studies, we compute the intersection of their precedence relations. Here, for example, is the intersection of the Taliban case and that of the Democratic Republic of the Congo for the years 1998 to 2003. This is the subset of precedence relations that connect variables in both cases. Thus, the beginning of the orderings in both conflicts was favorable to the respective government, V38 and V46. Eventually, each insurgency featured actions of one or both sides that precipitated or constituted ethnic or religious violence, V74. In Afghanistan, the conflict was between the largely Pashtun southern regions, highly sympathetic to the Taliban government, and the northern Tajiks, Hazara, Kyrgyz, and other ethnic groups. In the Congo, the conflict was entangled with the DRC's ethnic antagonisms between Hutus, Tutsis, and other groups. Following the ethnic conflict, in both cases, were events favorable to the respective insurgents. Government forces failed to adapt to changes in tactics or operations of their adversaries, V53. Insurgents delegitimized government forces, V56. External military forces, the US in the Afghan case, and a number of neighboring countries in the Congo case, fought on behalf of the insurgents, V64. And the insurgent forces were more professional than those of the respective government. Finally, whereas this slide depicts the intersections of the event orderings, we can also learn a great deal from the disjunctive union or symmetric difference, which is revealing of the distinctive features shared by only one case, but not the other. For example, the Taliban government in Afghanistan was able initially to maintain a perception of security among the populace in areas that it controlled. This was shown earlier for the Afghan slide. In the disjunctive union, this feature does not appear, and therefore that reveals that it was not operative in the case of the Congo. To compare cases, I've introduced the intersection of event ordering. So the union is a similarly defined concept. The well-known Jacquard coefficient is the ratio of the intersection to the union, in this case of the event orderings of our two insurgencies. Sorry. Yes, so here the Jacquard coefficient measuring the similarity of these two cases, the Afghan Taliban and the Congo case I've reviewed, is only a moderate 0.23. We can also look at the distance of each of the cases from the intersection. So if the intersection is a common representation, then we can say we discover that the intersection is a more faithful representation of the structure in the Afghan case than it is in this example of the Congo case. The Jacquard similarity coefficient is higher with respect to the relation of the intersection to the one case versus the other. And a network of insurgencies may be created with relations among insurgencies, measuring the degree of overlap among their sequenced activities. Jacquard coefficients among all pairs of the 30 event orderings, one for each case study, are shown in this slide. Cases are named using 3-digit ISO country codes when they're available. And the years of the conflict are distinguished for multiple cases occurring in the same country. It's possible to visualize this network of cases connected by phase precedence among the variables. And here, the Jacquard coefficients among an arbitrary threshold are shown. In a working paper, we have investigated and found robustness across a wide range of cutoff values. Node coloring indicates the outcome of these 30 insurgencies, as those outcomes were coded by the original RAND researchers. There are two especially remarkable features of this diagram. First, cases of government wins, these are nodes colored blue, tend to cluster together in the network at the top of the diagram, indicating their closeness in Jacquard space. The remaining cases, coded by the RAND team as insurgent wins, the red nodes, or mixed cases favoring the insurgents, the gray nodes, are intermixed with one another. A second remarkable feature of this diagram is that the case of the Nicaraguan Contras is easily identified as an anomalous case. This case, the only red node at the top of the slide, NIC 86, 1986, was coded as an insurgent win, but with many of the inclusions common as well to the government win cases. I will discuss this detected anomaly in a subsequent slide. A very important feature of our approach is that we can identify a backbone structure or an analytic narrative of inclusions that are common to all the cases coded as government wins, or for that matter, of any other subset of cases. Here, we find the backbone of an analytic narrative of government wins. First, government forces do not employ culturally inappropriate outsiders, V44. Then insurgents demonstrate potency through attacks, V54. Then next is a branching process. On the one hand, coin forces build up strength, V69. On the other hand, the government forces, on the other hand, insurgents engage in behavior that's unacceptable to the populace or cause large civilian casualties, becoming delegitimized, V59. And flows of insurgents from across borders are, the government is able to decrease those. So these are precisely the features that are common to the 8 cases coded as government wins by the RAND researchers. And in this sense is a backbone of the narrative of those cases. Turning to the common features of insurgent wins, these are 14 of our cases. 2 variables, which are equated to each other, are common to all these cases. Insurgents demonstrated potency through attacks, V54, and government forces employed collective punishment against the populace, V26. While admittedly, this narrative is not very rich, or indeed very sequential, the relative lack of structure shown in this slide suggests a next analytical step, that it would be productive to not treat all 14 insurgent win cases as homogeneous, but instead to seek clusters of cases within this set of 14, but with each cluster presumably exhibiting richer structure. Now, concerning the anomalous case of the Nicaragua Contras, in brief, it's anomalous because it exhibited little variation across time periods. For each of the 3, most of the variables that were present in any of the 3 time periods as coded by the original researchers were present in all of those time periods, and hence the temporal variation was minimal. The one exception being that the the government forces. These are the Contras who are being supported illegally by the American CIA, as described in the RAND report. The Contra forces were given shoulder-fired missiles that allowed them to shoot down government helicopters, and the Contra government prevailed in this case. Okay. So an important literature that we would like to relate to is the work on narrative of Peter Abel, which I've discussed earlier. And as I mentioned earlier, our approach is quite different from his. We're dealing with many cases simultaneously. We have a very different formalism, but we share with him and we're inspired by him with the motivation to use network studies to seek an alternative to variable-centered forms of analysis. So we think it's possible to use conventional variables of the sort that are used in survey analysis and in other work that I and colleagues are involved in, regression analysis, as the material for useful network formulations of social phenomena. And our work on precedence orderings and partial orders of event sequences is an effort to take the material of variable-centered analysis and to use it, harness it instead to network or relational thinking. In conclusion, I would emphasize that all the empirical work that I've reviewed is meant primarily to explore and to illustrate the kinds of analysis that we think can be envisioned and carried out in contexts like ours. Many decisions we have made need to be revisited and rethought as to possible alternatives. For example, we could study the presence of a variable at phase K as leading to the absence of some other variable at phase K+1. We could look not at which events precede others, but at which events follow others, which would lead to a different representation. We could try to predict the final phase of each case from the phases that preceded it. Okay, with those qualifications in mind, I would nonetheless like to emphasize, as the slide suggests, that one productive way for analyzing an insurgency is to view it as a network of sequenced variables across stages or periods of the conflict. A network of insurgencies may be created with relations among insurgencies measuring the degree of overlap among their sequenced activities, as in our network of Jacquard coefficients. The network among insurgencies may be informative as to sequences predicting outcomes of interest, such as winners and losers in conflict. The sequences common to insurgencies of certain types, such as government wins, may be identified. That was the backbone that we identified with respect to the 8 cases of government win as their common intersection of precedence orderings. Anomalous cases, in our case, Nicaragua, the conflict beginning in 1986, may be identified and examined by using our approach. And then in future work, we'd like to predict without using what we'd like to predict a final time period without using it, but using only the subsequent periods. Okay, so thank you for your attention. I would welcome email comments, questions, and exchanges. I regret that the 9-hour time difference means that if it's on schedule, this talk will be presented at approximately 1:30 in the morning, my local time in Arizona. I'm sorry that limits my participation in this conference, but thank you again for your invitation, and I look forward to participating to the extent that I'm able to do so. Thank you very much.
Okay, so it was a great initiative to pre-record some talks. Okay, let's have now 10-minute break. Okay, let's start now with the talk by Professor Branislav Randelovic on algebraic tool for economizing the testing process in social sciences. Please, Professor.
Hello, good afternoon. Do you hear me? Is it okay? Okay, I will try to share my screen with the presentation. Just a few seconds. Okay. Well, I will try to present you our common work under the title An Algebraic Tool for Economizing the Testing Process in Social Sciences. Of course, not only social sciences, but it is, we put it here because it is in accordance with the title of our conference. And I'm speaking on behalf of our small team. I am professor at University of Niš, Faculty of Electronic Engineering, and also at University of M.Mitrović, the Faculty of Teachers Education. My colleague Melanija, you all know her, our host, chief of parade of this conference, professor on Faculty of Mechanical Engineering. Third author is Professor M.Mitrović from Faculty of Electronic Engineering. And the fourth one is our colleague Ivana Ilić from Faculty of Medicine, but also our colleague mathematician. And I will try to share with you in a few slides and to not go too deep in this topic, but to be easy for listening. First, I will share with you our abstract in modern social sciences, and wider in whole modern society, there are permanent needs for a large number of testing in almost all segments. On the opposite side, large-scale research or large-scale testing on a large sample can be very, very expensive. In order to reduce the overall price of testing, it could be useful to use some methods. We propose mathematical methods for choosing the appropriate sample. And use of the appropriate mathematical models should reduce the sample of testing and reduce overall price of testing. And also very important to give accurate or at least approximate and useful results that can satisfy needs. In this paper we propose one algebraic tool and mathematical method for selective testing using set theory and basic combinatorics. We select a sample for testing from different available groups using so-called system of distinct representatives. System of distinct representatives will be used in order to minimize overall number of testing using a permanent of incidence matrix. So the most important words here in order to reduce the overall price of testing. And in today's world, it is very, very important, especially when you have a large sample and a large scale research. So this presentation will consist of 4 parts. First, introduction. After that, I will give you just a few slides of mathematical background, what we are using in our method, a few slides with main results and example, and a conclusion at the end. So I will try to put everything in proposed 15 minutes. As you know, in modern social sciences and in natural sciences and wider in whole industry and modern society, there are permanent needs for large number of testings in laboratory conditions, in chemistry, in agriculture, especially regarding healthy food, and testing with animals, and why not to say testing with people, that should be and that are always very, very, very expensive when you have a large number of people to test on any subject. And large scale research of testing can be very expensive, and in order to reduce overall price, it is needed to use mathematical methods and to choose appropriate sample and to reduce the price of that testing. Especially interesting is our COVID situation that we are in it in the last 2 years, and we are witnesses that there are a lot of testing, especially if you want to travel from one country to another. You are obligated to pass PCR or other tests, and each of those tests is very, very expensive, and the overall price for states, for countries, and for the whole world is very, very big. And it is useful to let's say in that example, it is useful to have some tools or some algorithms to reduce the price. There are a lot of papers already published in the world regarding strategies and algorithms for sampling and less number of testing, and to get a reasonable result. And I found some of them, some papers and some projects that are already dealing with sampling and testing regarding COVID-19. Appropriate mathematical model should reduce the sample and overall price, but also give, if not accurate, but at least approximate, and I pointed out useful results that can satisfy needs of researchers that are implementing testing. So we already know, especially in social sciences, we have some usual ways for selecting samples, and I put several of them in next 4 slides. One of them is called simple sampling from a group. Of course, each of them has its own advantage and disadvantage. The disadvantage of this simple sampling is less precise than stratified method, less representative than systematic method. We can implement some systematic method, let's say to choose every nth particle, every nth member of the group. Stratified method of sampling is slightly better in some way, but it is not so easy to implement on big numbers. When you have a large number of people or who is tested. And I found was one way of sampling, so-called cluster sampling, and this is already known, and those are methods that are people and researchers using in various situations. But now we try to approach to this matter with a little bit more mathematics, and we use simple set theory and basic combinatorics. We will use matrices. I don't know are all participants of conference mathematicians. I think they are not, but I try to be simple in my speech. If somebody is not mathematician, that understand what I think when I said matrices, especially binary matrices. Binary matrices are with zeros and ones. We use one interesting but not so famous method in algebra, that is calculation of permanent of matrix. And as I said in the beginning, we use systems of distinct representatives known as SDR, and this is a method of planned sampling and choosing the members of subsets in some configuration. That is something like an introduction, what will be used to make best sample and minimize sample and minimize the cost of research. What is mathematically beside all this thing that we are speaking about? Set theory. We all know that set is one of fundamental terms in mathematics. There is no definition by intuitive approach. Set is an arbitrary but precise described totality of suited objects. So we can use set theory in each area of social or other part of our livings. We can, of course, precisely define elements, but in several ways. But enumerating elements by property of element or by procedure. Connected with sets is some so-called combinatorial configuration or block schemes. And I tried with this definition to define a combinatorial configuration system of subsets composed of elements of a set. I'm risking now, because we all know whenever you use some definition, you cut the number of listeners to half, but I will use several definitions. I hope I will keep you until the end of this presentation. Example, set of subsets on a set from 1 to 7. I choose one simple example. There are subsets S1, S2, S3, and S4 that are shown on this example. For any of configuration S1, S2 to Sm, we can define rectangular matrix of order m times n with 1s and 0 as elements. And this rectangular matrix is called incidence matrix for configuration, and we will use those matrices for calculation of number of samplings. Matrix representation of the configuration is very convenient because it is relatively well-developed matrix calculus in algebra, and dimensions of matrix can be same or different. This is one example of incidence matrix for one subset for one configuration of subsets. Another definition is what is binary matrix, but I will jump over it because I think it was clear when you saw a matrix with zeros and ones that are binary or Boolean matrix. Definition of permanent. How can we calculate permanent of one square matrix and permanent of one rectangular matrix with condition that M must be least or equal n number of rows, less or equal to number of columns. And this is one simple example for calculation of permanent. The last term that I will introduce here is system of distinct representatives. If we have a configuration S1, S2 to Sm over the finite set S with n mutually different elements, a subset S1, S2 to Sm of mutually different elements with the property that S1 is element of S1, big S1, Si element of Si, for I goes from 1 to m, is called a system of distinct representatives for a given configuration. Easier to explain, to take one member of each of those subsets. And this is the way how we can make our sample out of many members of originally set. The total number of systems of distinct representatives, this is very important, the total number for given configuration over a set S of n mutually different elements is equal to the permanent of its incidence matrix. And that's the core of our thinking, to use distinct representatives, because permanent of incidence matrix is the number that is much smaller than all possible ways of sampling the elements of sets. So we came to the main result that I will give here without any proofing, just to share with you. If there is a need to implement some research on a large-scale sample, that includes a large number of testing on a set of n elements, and if it is planned to conduct testing on a smaller sample using a system of distinct representatives, number of testing can be reduced from n factorial to permanent of incident matrix A, where A is incident matrix for a system of distinct representatives of some configuration over the set. In that case, permanent of this matrix should be much smaller than n factorial. It does the way how we can reduce the overall number of sampling, of testing, and to reduce the overall price. Let's try to show it on some example. Suppose that we should implement some testing on a sample of 5 persons, where in the process of testing is important to treat them in combination as a team. And each of them can be in any of 5 testing positions in a team. And each place in testing team can be filled with 3 out of 5 persons. Is it possible to implement such a testing? And if it is, how many different ways of testing is possible? We have 5 persons, of course. Biggest possible number of ways of testing is 5 factorial, it is 120. But will it be smaller? Of course. We will use system of distinct representatives. Let's build a configuration of 5 subsets over the set S, 1, 2, 3, 4, 5, and each of subsets will consist of 3 mutually different elements. Arbitrary choose, let it be arbitrary choose. Each of elements must be in exactly 3 different subsets. I will give one example of that. Let's see this configuration. So numbers are related with persons from that set. Let's build incidence matrix for this configuration. Incidence matrix is binary or Boolean. And as you can see, we have number 1 in each row when we have appropriate person in this subset. Let's say in subset S1, there is one first, second, and fourth person. So in first line, we have first, second, and fourth 1, and the others are 0. Let's find permanent of this matrix. If we calculate permanent of this matrix, it is 13. And you will agree with me that 13 is overall number of all systems of distinct representatives. So it is minimal number of all testing combinations. And we can even find all testing combinations. I will not go inside of this because it is a little bit complicated, but there is an algorithm to construct each of them. So we found a way how to make 13 different testing algorithms, testing combinations, in order to get some result instead of originally 5 factorial. It is 120. And of course, you will agree that 13 is much, much less than 120. And this is something that we will work in the future period to extend this idea and to put it in algorithmical way, and to show that this could be very useful in various way of research and testing. So thank you for your patience. I will conclude with another sentence. An overall number of tests in some large-scale research on a set of n element, where is planned to conduct testing on a smaller sample using a system of distinct representatives. Number of testing can be reduced from n factorial to permanent of a that is much smaller. And I hope I didn't bother you too much. Thank you very much on behalf of our small team.
Thank you, Professor Rangelovic, for your nice talk. It is now my pleasure to invite Professor Dragana Martinovic, one of the main organizers of this conference, to give her talk on algebra and modeling in mathematical school curriculum. Please, Professor Martinovic.
Thank you very much. Do you see my screen?
Yeah, it's fine.
Thank you. Okay, first I will apologize for my voice. I had last week I had major dental surgery and I'm still learning to speak. So I apologize to you. I will bring you back to the school, and some of you may have children or grandchildren even, and you may know about school mathematics, but this is the topic of my talk, and I think you will find it different. So this is what I will be talking about. I'll be talking about place of algebra in school mathematics, how to teach early algebra, what it is, and what is algebraic reasoning. And then I will walk you through different examples of algebra tasks from school and also modeling examples. And then in conclusion, I'll be talking about what is missing in the curriculum. And I will mostly talk about North American curriculum, and of course, particularly curriculum from Ontario, where I live. I'm professor of mathematics education at University of Windsor, and I teach future high school teachers of mathematics. So I will first start by defining place of algebra. As Marcel Danesi spoke about, he said that first in schools we start with arithmetic and then we go into algebra, but it doesn't have to be so. And especially it is problematic that in some national curricula, especially in the United States, because every state has its own mathematics curriculum, algebra is actually taught as algebra 1, 2, 3 in high school. So by having that way of positioning algebra in the curriculum, it allows students to miss algebra because they can take something else instead. And that's, of course, problematic. So nowadays, educators agree that it should be taught, algebra should be taught from grade 1. John Mason, a mathematics educator, claims that even arithmetic without generality is a purely clerical activity. Arithmetic, which calls upon children to become aware of generality, is mathematics. So what I want to talk about is actually how to, through arithmetic, to start teaching early algebra and developing that early understanding of important terms that students will be picking up later. John Mason believes that it is never too early to learn to think algebraically, and he calls for sensitively directed generalization and abstraction. So I want you to pay attention to these two words, generalization and abstraction, and of course they are in the core of algebraic thinking. Sensitively means that teacher has always to have in their mind where the student is, and so that, you know, provide the best activities for that student. James Caput considers algebraic reasoning among the most powerful intellectual tools and tools around algebra that our civilization has developed. And Caput is also one of many who fought to infuse algebra throughout curriculum from the very beginning of school. One of the journals, the Mathematics Teacher, is a journal for teachers of mathematics, wrote in their editorial, "It is true that the value of algebra in public education is not as obvious as the value of arithmetic." And they asked Zalman Rusiskin, another famous mathematics educator, to explain why it is important to learn algebra. He said that first, algebra is the language of generalization. It can describe relations, rules, and patterns in a concise form. It enables a person to answer all the questions of a particular type at one time. And I love this quote, because for me, it is the essence of algebra. So in school, of course, first students start with arithmetic, you know, properties of counting, whole numbers, fractions, and then basic operations with these numbers, followed by algebra that is usually associated with the use of letters as placeholders for something else. Now, as Marcel Danesi said, usually algebra is thought of as arithmetic plus letters. And of course, it is wrong, and it is not enough, as previously I showed on these slides. So in arithmetic, we would say that the result of adding one number to another doesn't change if the order is reversed. In algebra, this is how we would write it. And I vividly remember one event in my early schooling. I did my schooling in Belgrade in Serbia. I was probably in grade 3 or 4. I don't remember that part. But I remember when I first realized then mathematics can be done with letters. For me, that was the major aha moment in my life, and probably one of the moments that decided that I will become a mathematician later. So how true of this. So I want to show you how we teach early algebra, or teachers can teach early algebra to children. For example, they can notice patterns and properties. And as Wozni was saying, we are so good with making these connections and realizing different things. So it could be done with numbers. For example, guessing the next, if following the pattern, what would be the missing numbers. Or students can play with matches and create different objects and think how the next object differs from the previous and what will be the next one. Or in this example here, again with matches, they can think about what is the same, what remains the same, and what is different going from one to another. The next example here is a little bit more geometrical because it speaks about also different properties. So each object in this sequence has its geometrical form, so square, circle, triangle, but also is shaded, can be shaded. So the student can be looking only into shading and recognizing the pattern, shaded, not shaded, shaded, and so on, so that they can guess here that it comes not shading. Or the student can look only into geometric form, thinking that after the square comes a circle, or they can look into both properties at the same time. So that is, as you can see, extension of the previous thinking. Or in geometry, this is again how we did algebraic reasoning. In geometry, you have asymmetry examples. So you are asking students, like they were doing here with numbers, to create missing patterns so that the whole image here is symmetrical with respect to this line, for example. I like this quote of Mason and colleagues who said that a lesson without the opportunity for learners to generalize mathematically is not a mathematics lesson. And I think that is something that teachers should really understand deeply, that even when they are working with numbers, so in arithmetic, they need to teach students to generalize, which is a major thing in algebraic thinking. So they're saying merely performing operations as algorithms is not mathematics. And that is what, again, Marcel was saying in his talk. He talked about pre-math, math, and then mathematics, which is something that I really love. So I want to show you some examples how even in arithmetic, students can learn to think algebraically. So let's say that they need to multiply 49 by 51. And they can recognize that actually the task is to multiply 50 minus 1 by 50 plus 1. Again, using just operations and working with these operations, they can recognize, something that we know is a difference of squares. Or recognizing that actually 87 plus 54 could be represented as 84 plus 57 without changing the value. So that is what thinking algebraically looks like. Here are some main themes in school algebra. So again, generalizing, related to patterning, noticing different properties, operations, and structures, using alphanumerical notation, manipulating expressions, and so on. So these are some early examples of algebra tasks. You see, noticing the role of zero, for example, noticing the role of opposites in the expressions. And this is one example, also interesting example. Students may be asked to multiply 5 by 5 and compare it to 4 times 6. 8 times 8 and compare it to 7 times 9. And what do they conclude? So similar to what I was talking about before. But the same example could be actually done geometrically, using a square as an example and asking students to change the square 3 times 3 into the rectangle 2 times 4 and compare the areas. Obviously, the area is multiplication. So you move from one multiplication arithmetic example into a little bit geometric example. So moving between these different domains of mathematics, again, brings about algebraic thinking. Of course, generalization is what happens when you change the square side length by 2 or by 3 or by more. Similarly, these calendar exam investigations are something the students love. You ask them to notice any patterns. They can notice them horizontally, vertically, compare cross products and so on. So very similar example to what I was showing you before. In high school, in grade 9, which is first grade of high school in Ontario, students learn to learn linear functions. And you can ask them to sketch these 2 linear functions. And then ask them what is the difference between the graph of f of g of x and f of x times g of x. Of course, you know from experience, the students often replace these 2 and cannot distinguish the 2. And this is a very easy example where, especially when moving from linear to quadratic equation, they start noticing these important points on the graph, which on the parabola, which are the consequence of the values of the other 2 graphs. So this would be one example. Another example that I want to share with you is a model, a number line, as a very powerful model for algebraic expressions. Now, on the number line, you can present variables, inequalities, absolute values, distances between numbers, and equations with absolute value. And for me, as a teacher educator, it was very interesting, this quote from Thomson and Carlson, who problematized notion of a number line as a line full of numbers, which is probably how we teach number line to students. Alternatively, number line may be presented without numbers, but full of positions, which is crucial for understanding numbers as magnitudes and developing understanding of continuum. So this is what I want to show you as an example. So this is one example where we can use a number line. There is only 0 there, so there are no number. I don't have units, I don't have anything, and we work with letters. So the task is draw number line, plot A and B, and we need 0 because 0 defines if the numbers A and B are both negative, both positive, or whatever. And then students may be asked to identify these positions. So let me show you this video. So the student can position A anywhere. So they obviously want A to be negative. We don't talk about values of A and B. B can be, again, anywhere. So obviously B is positive. Then if A is here, then obviously minus A has to be reflection with respect to 0. The same thing with minus B. Minus A is reflection of minus A, which actually puts it into where A is. And you get the idea, of course. The other task that I want to show you, again, how I work with the number line without numbers. Again, there is only 0 there because I work with the coordinate plane. This is the image that is not very clear because it's the image of my blackboard in my classroom. So the task is to identify on the coordinate plane the top right vertex of a rectangle having the area of 36. And there are no units, so here we have 2 coordinate axes, and of course we have 0. This is the width of the rectangle, this is the height of the rectangle. I'm sorry that is not very visible. And I start this exercise and I say, I will put my vertex here. This is what I imagine. And of course, you can see that the rectangle is here. So this rectangle, in my imagination, has area of 36. And then I ask the student to come to the board, and find another point for their imagined rectangle. And then we conclude that there are areas that are forbidden for other rectangles or vertices to be. This is forbidden and this is forbidden. Because if they would put vertex here, the area of that rectangle would be smaller than 36. If they put it here, it would be larger. So they have to find it somewhere else. And of course, and then you see how the whole thing develops. But the idea is, without having units on the number line, you actually create these very powerful images of the meaning of relationship between variables. In this case, between height and weight of the rectangle with the constant area. And of course, you know that this process builds a hyperbola, y equals to 36 over x, where x is greater than 0. And you can see that here we have these rectangles. I only put some numbers of coordinates with integer values, but you see these rectangles, and students develop that idea of what is the functional relationship, as Jacek was talking about. What is that mapping about? Number line is a very powerful model for vectors as well. Similar to what Jacek was talking when he was mentioning moving a stone. Imagine moving a stone across a particular direction. That is how we can introduce addition of numbers or subtraction on the number line when you use vectors, and that idea of moving across. That is actually the initial understanding of building initial understanding of vectors for our students. Another one that I wanted to show you how we can use number line as a model is actually using a double number line, which is very useful for presenting relationships such as linear relationships, y equals to kx, where k is a constant. So here you have a train that runs between 2 places at a uniform speed of 45 kilometers per hour. And on one number line, you present time. On the other number line, you present the distance. And you see that, especially if you use the same distance between these important mapping points, you see that these lines are parallel, actually informing students that there is a linearity between these two, or linear relationship between these two variables. So as you can see, a double number line is actually horizontally put a table of values. But table of values for me is so static. This double number line is more dynamic, as Jacek was talking about in his speech. Similar approach I used to visualize the train problem, and I will just show you quickly. This is the example. You know that students usually don't like those kind of problems, there you have two trains and one is faster than the other and one starts later. The question is, when is the faster going to pick up with the slower, and so on. So I will show you how I do that. I introduce parametric functions to do this problem. And using parametric representation, students see exactly how these two trains move and when the faster one catches up with the slower one. And then we can investigate different positions and so on. I just made the video for easier representation. And then we compare it to the usual time distance graph. And then we see how different these representations are. And they answer actually different kinds of questions. Here, position of Windsor, which is the starting point for our trains, is very obvious. It is on y-axis. But here, when I ask them, where is Windsor here? It's not very clear for them to answer. So they struggle with that one. But anyway, both are interesting. In conclusion, I want to just mention, you know, when I was listening for all these talks, it was so striking to what extent mathematicians always cite other mathematicians. There is so much appreciation for work and effort in the community for what others are doing, because we always build on others. In school curriculum, that is not the case. There is only one mention of the word theorem in Ontario curriculum, and that is in relation to Pythagorean theorem. Only once. Another mention of mathematicians, so Pythagorean theorem or relationship, Fibonacci series, Pascal triangle. But I think that students more know about Fibonacci rabbits than about Fibonacci. They know more about this image than about Pascal. And of course, this is a semiotic metaphor, as Jacek would say, metaphor for Pythagorean theorem. Again, very limiting for Pythagorean theorem. But there is no mention of the Descartes, Diophantus, Viet, Kramer, and all sorts of army of others. What is missing in the curriculum are mathematics in induction, history of mathematics, and stories about mathematics. And I see that problematic. In conclusion, algebra has a prominent place in the curriculum, but it is left to teachers' knowledge to make it a relevant connection, select the task, and inspire students. Algebra learning should start early, and of course, models and modeling are crucial, as we saw in this small number of examples. And of course, students need to experience more complex and modern mathematics. To finish with my presentation, I will just complete the citation from James Caput, who said that without algebra, there could not be higher mathematics and no quantitative science, hence no technology and modern life as we know them. Thank you.
Thank you, Dragana, for your very nice, very instructive talk. It is very useful and probably based on IBSC method, and this could help sharing best practice in math training, math education. It's very, very, very nice. I'm really interested in. So now, I'm pleased to invite Professor Melanija M.Mitrović to give her talk on constructive semi-groups with apartness, the state of the art. Please, Professor M.Mitrović.
Okay, thank you very much, Professor Hounkonnou. So we created and we developed theory of constructive semi-group with apartness. Exactly, we did it. And we are still doing that. But is it art? So, although frequently fragmentary studies of semigroups carried out at the end of 20s of the last century are often marked as the beginning of their history. In the era without fast communication devices, semigroups took their place in development of their other mathematical disciplines pretty fast. In front of you is the paragraph, actually the first paragraph from the foreword of this book. And the part of the poem, which was given in the previous slide, is actually quoted as an epigraph before this foreword. So we did it. Our theory is, of course, partially inspired by classical case, but it is distinguished from it in two significant aspects. We used intuitionistic logic rather than classical. Our work is based on the notion of apartness between elements and sets. It is Hating who wrote in his famous book Intuitionism, an Introduction from 1956, that in order to build up a definite branch of intuitionistic mathematics, it is necessary in the first place to have a true knowledge of corresponding branch of classical mathematics, and in the second place, to know by experience where the intuitionistic pitfalls lie. Having Hating's word in mind, we brought to speak of 2 points of view on a given subject, classical and constructive. Our theory provides one of the most basic tools for classical semigroup theory. This is very well-known fact. Completely normal and quite natural development of an appropriate constructive order theory for semigroups with apartness was and is one of the main objectives of our work. As for classical case, of course, the order theory always begins with sets. Mentioned several times during the conference, set within classical mathematics is considered to be primitive notion which one does not define. Talking about their applications, order and order structure enter into computer science and into humanities and social sciences in many ways and on many different levels. The most basic concepts of order theory leads to quasi-orders, reflexive and transitive relation. Quasi-ordered and quasi-ordered sets are in the core of order theory. Well-known facts from set theory, equivalences, and first isomorphism theorem, formulated by the helping of them and proved, of course. But if we have a quasi-order on a set, for example, rho, then we can associate an equivalence to it. And as a next step, we can obtain an order set using that quasi-order to define the order on the quotient set in the following way. Well-known result as well. Talking about semigroups, congruences, again, very well known, elementary knowledge, that congruence played the very crucial role, and the isomorphism theorems are based on congruences defined on them. But if we have an ordered semigroup, congruences are not enough anymore. It can be a case that for a given congruence on ordered semigroups, quotient semigroup need not be ordered semigroup anymore. So we have a problem. And that problem is solved in 1995. It is noticed that beside the Congress, we need help of some kind of, certain kind of quasi-order called nest quasi-order. The result from 1997, given here, we little bit modified it. So you will see later, then developing our constructive order theory, we faced with almost the same situation. The structure of our semigroups is not automatically translated to the quotient or to cofactor semigroups. So the first phase of my work on semigroup theory was classical case. I end this case after this book was published, and 14 years later, in 2017, working on this paper and investigating in more detail possibilities of applications of our favorite structure, I discovered book of John Paul Boyd, Boris Shine review on that book, Pip's book, etc. So, constructive case. There are a lot of decisions mathematician has to make when decide to replace classical logic with intuitionistic one. Step by step, I am going to explain one after another decisions which should be made, and what those decisions are all about. First of all, we have to choose a variant of constructive mathematics. You know, constructive mathematics is not unique notion. Principal trends include the following varieties: Brouwer intuitionistic logic, constructive recursive mathematics of the Russian school of Markov, Eric Bishop style of constructive mathematics. What is common for all those varieties is that they are based on intuitionistic logic. But on the other hand, different form can have different additional principles or axiom. For example, the notion of an algorithm or finite routine is primitive for Eric Bishop's mathematics and intuitionistic Brouwer mathematics. So our choice was to work within Eric Bishop's style of constructive mathematics. Why? Eric Bishop's style of mathematics, what is done within Bishop style mathematics, it is valid in all other constructive varieties. It is valid as well within classical mathematics, which is not the case with other constructive varieties. So let's go further. The cornerstones for Bish include the notion of positive integers, sets, and function. And guess what? Sets are not the primitive notion anymore. We have to define set. And in order to define set, we must have those two pieces of information: a property about or algorithm how to construct members of S. Remember, algorithm is the primitive notion in Bish, and we have to define equality, at least to explain what does it mean to elements of set be equal. Then another source of trouble, and this is the point, and this is what Hating means when he wrote that having experience where the intuitionistic pitfalls lie is very important. Splitting of notions, phenomena is how to say, knowing that phenomena is very important in the first place because of defining the terms in a right way. classically equivalent notion often split into a certain number of inequivalent constructive ones. For the beginning, the most important example for our further work was inequalities. There are different types of inequalities: denial inequality, diversity, apartness, tight apartness, some of them completely independent, which only in class are equal to one standard inequality. So, to conclude a little, to make some kind of a conclusion, if one can expect that the splitting of notion leads to enormous profilation of results. In particular, this is not so. In particular, usually only very few constructive versions of a classical notion are worth further development. As for choice, so we have to choose inequality. Apartness is the second most important relation in constructive algebra, in constructive mathematics, especially in constructive algebra. Apartness is a binary relation on a set which is reflexive, symmetric, and cotransitive. If, in addition, we have the following connection between equality and apartness, we call such apartness tight. So here again, we are in front of the choice. There are different definition. What does it mean, set with apartness? Set with apartness is a starting point in when working constructively. Of course, there are several definitions. It depends on connections with relations which are present between set and apartness. And again, faced with the choice, we choose. Our choice was our set with apartness to be with equality and apartness as a basic notions, defined independently on one of another, and with apartness which is in general not tight. Our choice was and still is the novelty within constructive circles. So again, very important example of splitting of notion. A subset of a given set with apartness has two complements. Beside well-known logical, here we have apartness complement as well. Using two complements, we distinguish three types. We can distinguish three types of subsets: so-called detachable, strongly detachable, and quasi-detachable subset. It happens again that those type of subsets shows up very important in developing our constructive order theory. In meantime, we given a name co-ordered, constructive co-order theory. It is just for now the case. And in order to moving up and to make our knowledge about this more to grow, it was very important to describe relation between those three subsets. For a long period of time, we were able to give partial relations. And that is improvement of our development of our order theory was going in a very slow way till recently. It is our results, Hounkonnou, Baroni, and me, from the beginning of last year. The result can be found in this reference, where we managed to give complete description of the relationships between those three types of subsets. For example, any strongly detachable subset is a quasi-detachable subset. The converse implication entails LPO, limited principle of omniscience. For any quasi-detachable subset, we have that two complements coincide. If any quasi-detachable subset is a detachable subset, then LPO holds. If any detachable subset is a quasi-detachable subset, then MP holds. Any strongly detachable subset is a detachable subset of S. The converse implication entails MP. If any subset of a set which apartness is quasi-detachable subset, then LPO holds. And I assume that at this point, I have to give maybe more information. What does it mean that statements, what is mentioned here actually in this theorem, what does it mean that statements imply or entails LPO or MP? And what are very important notion in constructing mathematical way of proving what are exactly the principle of omniscience. The principle of omniscience within constructing mathematics are statements which are considered to have no proof. For example, law of excluded middle and its equivalent forms. LPO, limited principle of omniscience, and Markov principles are considered to be examples of principles of omniscience. So the statement, for example, the statement T cannot be proved if you want to show that the statement T cannot be proved, then we have to show that statement T implies one of the omniscience principle. So I hope so that I gave some kind of relation. And why those subsets, those type of subsets are so important? Because known facts accepted from classical mathematics, we can define the binary relation as on a given set as a subset of Cartesian products, S times S. And then we can, it happens that for our constructive coordinate theory, which we develop exclusively to manage to work within constructive semigroup seated partners, the main building blocks are actually, the relation which are main building blocks are actually quasi-detachable subsets, for which we have those nice properties. So that is very important for us to have this and to realize and to have especially this, that it is not possible that every subset of a given set is on that form, is quasi-detachable. So with these powerful results in our hand, which completely justify constructive order theory we developed, we moved further. So now we use strongly irreflexive and co-transitive relation called co-quasi-order as the main building blocks of our constructive order theory. In addition, if co-quasi-order is co-antisymmetric, then we have co-orders. So using that, we, of course, small comment about mapping, the definition of the mapping between sets, and it is very important to connect them with a partners relation. So with a co-quasi-order as a main building block, we define co-equivalence. Again, the similar situation as for order sets in classical semigroup theory. We faced with quotient structure problem. quotient semigroup here is not in general semigroup with a partners. So in order to define a partners, we construct co-equivalences, symmetric co-quasi-orders. And this is our result from 2013. In meantime, some other important results are also proven. For example, constructive version of so-called Birkhoff lemma. So if we have a co-quasi-order on a set with the partners, then we can associate in the following way co-equivalence on it, and then make cofactor set to be co-order set with co-order defined again by the helping of the initial co-quasi-order. Of course, for our next very, very recent results, which I'm going to present on next slide, this lemma, which can be seen as a consequence of Birkhoff, is very important. If we have strongly extensional mapping between two sets with the partners, then this relation is a co-quasi-order on S. Associate co-equivalence is part of co-kernel, and this should be written phi, of course it is mistake. And with these results in hand, as well as with first a partners isomorphism theorem for sets, we were able to, and we defined and we formulate and we proved a partners isomorphism theorem for co-order sets. Our very recent result is in front of you. So we called semigroup with the partners is a co-ordered if we define a co-order alpha on it, requiring alpha be co-compatible with multiplication on S. And then we, using Birkhoff, constructive version of Birkhoff lemma and its consequences, we formulated and we proved this result. And coming back to our recent paper, which is put in on archive in the August of 2020. Let me comment it a little bit. We put a critical review of the results from our already published papers on the constructive semigroup theory and contribute to its further development by giving solution to open problems, some open problems. As well as we draw attention to possible application in other constructive mathematics disciplines, in computer science, social sciences, economics, etc. So I'm very near to make my final remarks. Once again, to summarize, if we are going, if we, I, you, whoever, who are claimed to be classical mathematician, if we one day decide to change classical logic into Shainistic one, then let me list again the problems we will from the very beginning and in some step of our work faced with. First, we have to choose variant of constructive mathematics within our work and our investigation, which we will be. Secondly, we have to choose underlying structure, career set. Then we have to face with splitting notion phenomena. Be very careful in our definition. Guess what? It is not the case of splitting a notion phenomena for a notion. It is the case that we also have splitting notion phenomena for theorems, especially when we want to, in some way, translate classical theorem in constructive settings when we want to find a version of those classical theorem within constructive settings. We can face with our classical theorem to split in several constructive versions. We can face with situation that our constructive theorem will be with more with more assumption and with stronger conclusions. So then also well-known fact that constructive algebra is more complicated than the classical one. In which sense? We don't work with decidable quality. There are a lot of different type of structure we should face with. So is it simple? Is this simple? Is it more easier to work within constructive mathematics than within classical mathematics? One does not develop constructive mathematics due to simplification. There is something else, something so important, worth that simplicity can be sometimes sacrificed. So why to work constructively? Is it usefulness in question or something else? So instead of answer, here is, let us cite Hating again. It seems quite reasonable to judge a mathematical system by its usefulness. In my eyes, its chances of being useful for philosophy, history, and the social sciences are better. In fact, mathematics from the intuitionistic point of view is a study of certain functions of the human mind, and as such, it is akin to these sciences. But is usefulness really the only measure of value? You know how philosophers struggle with the problem of defining the concept of value in art, yet every educated person feels this value. The case is analogous to the value of intuitionistic mathematics. I started this presentation with a Rudyard Kipling, part of Rudyard Kipling poem, and I'm going to finish it with a part of his poem, If. His poem, If, is considered within professional circles and within readers as one of most impressive poems from the last century. So if you can dream, if you can think, if you can, then, if we can, then in the end, one day maybe we will present certain type of application of this theory. In meanwhile, while working on these connections with other sciences and try to make some kind of joint team in order to talk about and develop some kind of application, we will proceed to work on growing our theory. So thank you very much for your attention. At the end, let me say 1-2 sentences more. During this conference time, we present you lot of niche historical heritage. We present niche festival, and we present how we make fun here in niche. We didn't manage to present niche restaurant, but we expect that you will come and have those experience by yourself. But what I think I have to show you is where niche actually was. Here is my country, and here is a niche, and this is the place from which we try to do our best this conference from technical point of view to work as best as it is possible. So southeast of Serbia, 250 kilometers far from Belgrade, with its own airport named Constantine the Great. So let us, Corona, go out and see alive. Thank you again for your attention.
Thank you, Professor Mitrović, for your nice talk. So our dream will be a reality, dream to visit your great city. We will come.
You're welcome anytime.
Okay, let's move without any break to panel discussion with three main panelists, Professor Dragana Martinovic, Professor Melanija Mitrović, and Professor Pilippa Pattison, to draw some lessons from our conference. So I invite you to take place and start the discussion. Maybe Professor Martinovic will start first.
I can, thank you.
You're welcome.
I will start with our politicians, our ambassadors. They reminded us of the importance of making mathematics accessible to all students and how diversity fuels innovation. And I really expect that some very interesting collaborations will start as an outcome of this conference. And also, Ambassador spoke about STEAM versus STEM. And I will just quickly tell you what I think about it. I don't think that STEM needs more letters. I think that art is already in mathematics, as many of your contributions showed. I remember Norbert saying that theoretical and applied mathematics should converge. We need to overcome silos in mathematics. I also recall how Volkov reminded us of identities that a graduating high school student should have in his or her backpack or mind, and that not all identities were made equal. Shanti talked about the role of dance in learning mathematics. In secondary school mathematics, we use gestures and movement to interpret transformations of polynomial functions, especially parabola.
Yeah.
And moving along. So regarding making connections between social relationships and algebra in the curriculum, we use the Shandcake problem, the birthday problem, combinatorics and sets. But I think it will be beneficial to introduce more ideas of human relationships that I heard from you, except friendship and family relationships. I think it was very inspiring for me to extend these mathematical representations of the social choices, such as dictator and vetor. I remember what Boricic was talking about, and help students better understand the concept of impossibility. Danase's talk inspired me to look at a transformation of a line, a semiotic artifact of a number line, as object without numbers, and moving it to an object with some numbers, and then all numbers, to a set of parallel and then vertical lines, as in the Cartesian plane. And I will finish with Vojny's talk about human mathematics. He talked about metaphors and representations in mathematics, especially in view of mapping, and how actually complex it is, and how it is important that we address these different kinds of understanding in our school curricula. So I will finish for now, looking forward to other contributions.
Okay, thank you very much. And I can add that making mathematics attractive for each student depends on the way we teach it. So sharing best practices in math teaching is very important in this direction. And thank you again for the talk you gave on such matter. Okay. Now, Professor Pattison. Pilippa? Pip? Pip is there? Pip? Do you see Pip?
You can't hear us, I think.
Is she online or not?
Thank you.
Okay.
Thank you.
Please go on. You can speak now.
He's frozen. Oh, there she is.
Her internet connection is gone.
Okay. So maybe.
My apologies. I think every time I'm meant to speak, the internet drops out. I stayed at work to prevent that. I'd like to make a couple of remarks, and perhaps unsurprisingly, from the perspective of a social scientist. I must say I've thoroughly enjoyed these 3 days. It's just been a wonderful opportunity to connect with lots of ideas from the social sciences, and the range of ideas across the social scientists who've participated has been extraordinary, and really touched on some of the deep roots of many conceptions in the social sciences. So whether by happenstance or design, it just has been a wonderful collection of contributions from those involved. But also on the mathematics side, it's been really wonderful to see some sort of very contemporary, but also I really appreciate the care that everyone's taken to allow us to make your talks accessible to those of us who don't spend our nights and days immersed in algebra. So thank you very much for that on behalf of all of we social scientists. But I think one of the nice and really wonderful things about this conference, and again, I think the ambassadors touched on the opportunity that it's when you bring together people who don't normally connect with one another. I've got an awful feeling I'm frozen again. Is that, can you hear me?
No, it's okay.
Oh, okay, good. You create an opportunity for lots of different connections that might not otherwise occur. And it's well known, this is really the power of networks. They create opportunities for interactions that change the sort of course of social events and ideas. And so it's just been fantastic, I think, and I hope there's a lot of time for reflection. I'm really glad the talks will be available on the web. But I think there's a strong likelihood that there will be connections that people make, and I hope they will reach out to one another to explore those opportunities, because perhaps more intuitively, you can see a lot of points of possible connection, and I think we'll all sort through those options over coming months, and I really hope we do. But that's just wonderful to create these new potential linkages, and that's fantastic. The second observation I'd make, I've really appreciated hearing about the constructive approach, and I really want to think much more deeply about that, particularly given the connections, as you say, to sort of human reasoning, and I think there's a lot to think about there. In fact, I think in lots of the talks there's lots more to think about. I think we've been exposed to an array of new ideas that will really kind of filter through our minds for over coming days, and I'm sure we'll be reaching out to ask each other questions. And I'll finish by drawing on one of my favourite quotes from G.H. Hardy, who talks, I probably won't get the words quite right, but he talks about the fruitful conception being a generalisation with a happy particularity. And it strikes me in thinking about all of the talks we've heard over the last 3 days. And as Dragana just emphasised, algebra is all about generalisation, but a lot of the interest comes out of the particularity. And I think, if nothing else, we social scientists have a lot of particularities to offer. And so, again, I think there's a lot of fruitful opportunity. So thank you very much.
Thank you very much, Pip. Now, Professor Mitrović.
Again. Okay, but now it is supposed me to say something in front of semi-group theoretician community, and not only in front of them, in front of all algebraists who use semi-group theory, and semi-group, if we are talking about associative algebras, are present everywhere. So let me address to you as a semi-group theoretician who work mostly on abstract objects, of course, and their relations, and who for the very first time meet glorious work done by the colleagues from social sciences, arts, and humanities area on the applications of the structure I like so much. It is not enough to say that I'm impressed by the quality and additional light which is thrown to them. I finally realized why Boris Schein was so impressed. So what to say? All these constitute, I can repeat maybe in some other words, all these constitute the stimulus to go further in the development of new ideas and reinforce existing ones through their applications in life field. On the behalf of local organizing committee, Center of Applied Mathematics of Faculty of Mechanical Engineering of Niš, Faculty of Mechanical Engineering itself, let me announce our open invitation to you to visit Niš physically when COVID-19 pandemics allows us to do this. Immediately after it allows us to do. So thank you very much for a nice talk from my side, from the side of us who are present here last days, for nice talks, for nice, how to say, being together.
Okay, thank you very much. Does anyone want to say anything more? I'm addressing to other people. Okay.
Shanti.
No? Who?
Shanti.
Shanti. I'm from India. Shanti from India.
Shanti. Okay.
I really want to thank Norbert sir, you, and of course Melanija, because of you both I'm here, and thank you for accepting my paper, abstract in fact, and I loved all the presentations. It was really nice. Some of them were eye-openers, and especially Dragana, I'm a big fan of yours now. Looking at thinking of algebra and introducing algebra to middle school is a very big challenge, and you the perspective which you gave was totally different. I'm going to follow those in India, and of course send you some of the findings what we see here. And it was wonderful to see how algebra can be introduced in this way also. And I'm trying in small ways to do with teachers. Now I really want to work with students also. Learning process. So right now we are into this conference, and
can
imagine the students who have. Hello. Yeah.
I have one suggestion. I'm sorry. I'm sorry that I interrupt you. I saw that people start to leave the conference, and I want again to make a common picture. So please show up, and then we can proceed. I'm sorry. I apologize for this interruption, but please.
Yeah, no, it's okay.
I saw that they are leaving, and
okay. Okay, sorry. I just wanted to say thank you. I got excited, so I started speaking. I'm really happy.
I'm inviting our our engineer from technical support to be with us as well. Yeah, thanks to Milan. He's the only one who is present today, but they were. Please show up.
Okay.
The camera is not working well.
We didn't start. Please show up. Show up in order to be able to make common pictures. If there is no, then say yes, Bert. When is Bert coming? Okay. Okay, thank you. Now we can, sorry, Professor Hounkonnou, but.
Okay, some words before closing this conference. I think, like you, that we attend our objective is to discuss the problematic of mathematics, social science, arts, and algebraic modeling, with a special focus on the role of semi-groups in social sciences, mathematization in particular. And all this thanks to the high level of invited and contributed talks given by top experts like you. We spent together nice time, and most importantly, we overcome and break the barriers artificially established between our different disciplines. We feel now close to each other in thinking and doing, improving by this way our being and living together. We set the foundations for interdisciplinary, for a better future for our disciplines, which need such a dialogue to face contemporary challenges. We can start now new collaborations. But how to maintain such a dynamics between sciences and transmit it to future generations of scientists from different disciplines? That is the question. One of the main lessons I draw from this conference is that sciences are not rigidly separable. For that, I'd like to share some ideas with you, which can be discussed later by emails. First, the success of this conference naturally suggests its continuation, at least on a periodic basis. The initiators of the conference agree on that. So it is not a new idea, but just a kind of confirmation induced also by the conference itself. Second, in developing countries, such as in Africa, and probably in Serbia too, there is no really such spaces of dialogue between scientists, experts in social sciences, humanities, natural sciences, and mathematics. So I would like strongly to invite you, my colleagues and organizers of this conference, Professor Dragana Martinovic, Professor Melanija, M.Mitrović, and Professor Pilippa Pattison, as well as other great speakers at this conference, to think together with me about the possibility of organizing summer schools on life sciences and mathematics for master's degree and PhD students from our countries, in order to offer them the opportunity to rethinking otherwise about science. Basis of what I used to call global science in times of complex challenges. So there are my great suggestion to you. Let's think together how to implement such summer schools. Now, on behalf of the International Organizing and Program Committee members, I'd like to thank everyone for your active participation to this wonderful virtual meeting. Also, on behalf of the organizing committee, on behalf of the International Organizing Committee, I say many thanks to all our eminent persons who accepted to be members of the program committee. My special thanks go to the members of the International Organizing Committee, Professor Dragana Martinovic, Professor Melanija M.Mitrović, and Professor Pilippa Pattison for the great job they did for the success of this conference. So, dear Dragana, Melanija, and Pip, I'm proud of you and proud to be with you in this adventure. Finally, allow me to present all our gratitude to the members of the local organizing committee in Niš, who did a splendid job.
Come on,
by
show you.
preparing.
Show you.
They did a splendid job by preparing and warranting all technical dimensions for the success of our conference. So they deserve recognition and applause.
So let me, sorry.
Let's unmute your micro and applaud with me.
So, engineer, Doctor of Technical Science, Milan Pavlović, today and all days was with us. Yeah. You communicate with him, he sent you reminders, and he helped you in making connection, making your records or slides be in front of you, and he has an additional information for you in connection with records and pictures. Of course, pictures. We will put a picture.
So hello to everyone. Thank you for your participating in this conference and for cooperation. I was the guy from Mat Socart host. So one information, recordings and pics will be available on a link, and you will receive email with that link in next few days, just to inform you.
Thank you. And be sure we are ready to visit your great city once past all these hard global times. So thank you again.
You're welcome.
Thank you. Thank you again. So our conference is closed. Bye-bye next time. See you next time.
Bye, thank you.
See you
See you.
next time.
See you in Niche.
Or somewhere else.
Exactly.
It is not excluded. Somewhere else, niche.
Yeah.
I can come whenever you.
In Benin, why not? Yeah, I collaborated with many colleagues from Canada, in particular from a university, Concordia University. Yeah.
So anyway, you will hear from us soon, and we are thinking also of the next conference.
Yeah, of course. We discuss it. Bye-bye.
Stay well.
Yeah.
Goodbye. Thank you very much.
Yeah, you're welcome.